on behalf of ICQMT 2022 committee. I don't know if you all know me, but maybe it's better for me to introduce myself. So I am Begüm Öncül. I am one of the organizing committee, like as a supermarket coming from supermarket company. We have so many overseas participants as plenary speakers, half plenary keynote invited, as well as oral and poster presenters. And it's also a great opportunity to have online participants after COVID pandemic. We are very grateful to all for the invaluable contributions and support. Thank you all for your participations. Hope you enjoyed the conference, and please also try to make time to visit Bodrum. It's one of my favorite places in Turkey. During the conference, we will be very happy to help anything you may need. Many thanks. And we have a terrible accident in Mine Cave recently in Barton. We have lost 40 miners. And I would like to invite you for a 1-minute silence. And now I would like to give the stage to Laura and Herman, so they will moderate the session for today. Thank you.
I'd like to introduce our first speaker, Ali Gencer, who will give us an introduction welcoming to the conference. He will also speak for the rector of Ankara University. I've known Ali for years as a wonderful physicist, and this conference, which has had many, many important impacts on human lives and science. So welcome, Ali.
Well, thank you very much to Laura, Herman, my dear daughter Begüm, and all the colleagues who come from different parts of the world and also Turkey. It's a great honor to have you here in the beautiful city of Milas and Bodrum together. Today, as an organizer, I would like to give you this talk, but I will probably stick only the first slide because the schedule is tight and our rector could not make it to come in person, and he is also very busy because on Tuesday there is a higher educational council meeting in Van, which is the other part of Turkey, and he's very busy. And he asked me to convey his great sympathy and regards to all the participants. And then after this talk, that should be about quantum locking, what you see in the first slide, then the president of our main funding agency, TÜBİTAK, the Professor Hasan Mandal, will be joining us online from one of the well-established institutions in Marmara, near Istanbul. Then we will have Valery as a distinguished scientist, and he's going to give us a very beautiful talk. So my talk will be just the introductory talk to Valery and our dear colleague Ahmet Avşar, and also dear colleague, professor and real friend, all-time friend, Laura Grini. And so Herman will be sharing together. And most of us know superconductivity is more than 100 years old, so that I can leave this place, I can walk like this. But maybe I need a laser pointer somewhere, if there is one, just to show. Okay. Okay. Well, the title of my talk is Impact of Emerging Technologies on Sustainable Development with R&D Progress. And there are global potentials of quantum technologies. Like superconductivity, quantum technologies maybe has two different eras we can talk about. It's the first era is first evolution of quantum technologies. That started with black body radiation in 1900 by Max Planck. So there are many distinguished scientists until 1940s made real breakthrough contributions to quantum physics. That has led to many outstanding discoveries. I think the most biggest one is maybe the MRI. Maybe the first one is diode and transistor. And transistors was invented in 1947 by Professor John Barden. He may be one of the guys who got twice Nobel Prize in the field of physics. And one was about the discovery of microscopic theory of superconductivity as BCS. We still rely on this theory, even after how many years? Let's say 70 years something. And by the time when we come to 19th century, end of 19th century, there were some misunderstood concepts that classical physics could not explain. Then this has led to birth of quantum physics. And the quantum physics has made significant changes in our daily life. I mean, this can go to transistor becoming integrated circuit chip and quantum processor eventually these days we are talking. And like superconductivity, many scientists, when it was discovered in 1911, thought that many things were possible, and it did not go because the need to cool down superconductors are a very essential issue. Like there is a need to cool down quantum materials to be effective in quantum technologies. Because in physics, in classical physics, we understand that the materials are not stationary. At the atomic level, they vibrate. And the only temperature we assume it is correct at absolute 0 Kelvin that they can stop. What does the quantum physics or mechanics say about this is that Heisenberg says if the position of an object is known more accurately, then you lose the accuracy in the momentum or the speed of it. And the Heisenberg maybe made a very accurate uncertainty principle that we still rely on it. But we actually do not know the momentum uncertainty when we really reach down to absolute 0 temperature. And this is maybe correlated to Bose-Einstein condensation, and I think the lowest temperature we have reached so far is about 38 picokelvin. Nearly 0, but pico is still non-zero value. And over the last 28 years, whether we can say the beginning of second quantum revolution as the discovery of electromagnetic waves passing through a fiber optic cable without attenuation. And this, in today's technology, possible up to 100 kilometers. So the fiber optic is an extremely important discovery of first quantum revolution to me. And transistor and GPS, even I am walking, my position is changes. So GPS also letting me know, somebody else also, where I am standing. GPS was militarily discovered, and Neven probably say more things about it. Then it has made for public use, and everybody on these mobiles, they get connected to base station and some satellites. They don't need to follow you. They can trace you whenever they want and where you were doing something good or bad. This is something else. But so quantum technologies now has already become the part of our lives daily. And it will go more and more. Eventually, quantum technologies will become a big, very important tool between the competitions of nations and making allies together. Maybe this is a not scientific way of thinking, but it will probably happen quite soon. The not very good competitions between the countries that will lead to, unfortunately, something that humankind experienced in the Second World War. The many scientists in the Manhattan Project worked heavily, and they did not get Nobel Prize for discovering the nuclear bombs, but they got it for making nuclear centrals for use in humankind. I think Enrico Fermi was Italian, then he was then later becoming American citizen. as the citizens of the whole world, we are very grateful to those great scientists, regardless of their ethnic origin or religion, because science is a common language between all people. As Laura said in the lecture for the school, it's very important that we teach people how to learn science and how to learn skills for negotiating. Yes? And we are very grateful for science. And science could be something that probably can persuade politicians not to do something that humans do not like in general. Therefore, we need to find the ways of persuading the politicians and use the scientific methods, not the old methods that brought the whole world in the nasty times during the Second World War and the First World War. So I'm not doing a scientific presentation, and so this is the first conference on quantum materials and technologies. And last year, in Dover, Herman and some other colleagues were talking that we should start a new conference on quantum materials and technologies because funding is going there for the last 5 years. After the announcement of the Nobel Prize a couple of weeks ago, and more funding will probably be devoted to the quantum materials and quantum technologies. It's a huge, wide spectrum area, and there are competition. There are technologies in competition, and I think superconductivity is one of the most versatile ones at the moment that are being used for quantum computation at the prototype level. So I'm just going to stop in 5 minutes because I think we are expecting Professor Dr. Hassan Mandal to be online on Zoom. So when he comes in the Zoom, just indicate and we don't make him to wait for more than a few minutes. So just 5 minutes, okay, I can see 5 minutes. Maybe in this conference I have a lot of gratitude to colleagues who have helped us with the selection of high-quality speakers all over the world, especially Valerie. We speak on the phone, WhatsApp, and Laura, Herman. And there are many colleagues that I could not make. Dover is here. And everyone needs special thanks from me, but if I forget something, and I seek your understanding. And and also Davron is here, Iman Hoca is here, Ali Bozbey, Haluk is here, okay? Not to mention all the names, but I think everyone has made great efforts to make this happen. Okay, so this is truly international conference, and we speak in English, and English is not a foreign language for all, it's an international language. And I thank you. I think I leave a few comments and questions from the audience. Thank you very much.
Thank you very much, Ali.
Yes, it's a pleasure. Okay, there is a question, by the way. Yeah.
I just wanted to thank you, Ali, for the organization, not just you, but everybody, because there's so many people involved. And it's very complicated to organize this, but I just want to prove the point you made, and it's not what I'm saying. I think it was the last lecture this morning in tutorials, yes. And we heard, and I'll quote it because I usually have information, but this blew me away. The Chinese colleagues and the Chinese government are opening a whole campus. I think the university is called Hefei or something like that. And they invested more than 11 billion euro. Now, I live in Switzerland, and we are solidly and regularly funded. European Union is way beyond, so is Germany and so on. So when you hear that, and there's going to be more, and the speaker was excellent, it was the last speaker in the morning, there'll be more at this conference. So when we go to our home universities or wherever we go, this illustrates the point. I can hardly remember, maybe Laura remembers when we had a high TC way back in '87, then it exploded, but not on this scale. I mean, rarely I heard that somebody opens just a full university for quantum technologies. And this I just learned this morning myself at this conference. So I fully support what you said. Thank you.
Thank you.
Do we have any other questions? If not, let's take Professor Gensler. So our next speaker is online, and it's Hasan Mandel from TÜBİTAK in Turkey, who will be speaking on cooperation and funding schemes of TÜBİTAK.
Okay. So, for the chairs and dear colleagues, ladies and gentlemen, so it's a great pleasure for me at least to be joining with you and then online. I am very sorry that I couldn't able to join physically, but I'll follow up the meeting with my consultants and which they are physically attending the meeting, and I'll do my best to contribute on online in terms of what is the importance and what type of potentials from the Turkey side. So once more, so I'll very welcome to Turkey, especially for our international participants, and also our Turkish colleagues who are attending, and also especially the young scientists and students. So they're very welcome to the meeting and the conference. So I'll share my contribution as a short presentation during the allocated time. So I'll switch to my presentation. Now, I guess now you will see my screen, and if not, just please let me know. Okay, and I put a title on quantum technologies. I think it's clear on materials and technology side, and I'm a material scientist as well. So and to put it as developing and succeeding together, because we have been many challenges. But at the meantime, the potentials, and one of the important potentials for overcome with this type of challenges is the quantum technologies. And so in this slide, on the screen that you can see by the World Economic Forum, for the next 10 years, the type of challenges which we are facing. And especially, the x-axis is the likelihood and the y-axis is the impact. So right hand, the top corner, so it has been listed on the left-hand side. So for the next 10 years, in a global sense, so what type of risks? And this was published in very early year 2021. So, we have been facing with the COVID-19, but some other type of challenges that time, which we have been just naming but not faced during that time. So which means, but when I am naming this type of challenges, so the still epidemic diseases, this could be, maybe not COVID-19, but some others will be in our agenda for the next 10 years. And the green ones in here has been named, so different type of topics on the climate change type of actions, but unfortunately the failure of the governments and also the loss of biodiversity, extreme climate events, the flood, fire, heat waves, storms, natural resources crisis, especially the food security, water security. So these are, unfortunately, this is a part of our life, and will be more and more in future, especially, I mean, has been named in next 10 years in here. And cybersecurity is one of the important agenda also, and social cohesion, erosion, the forced immigration, debt crisis, prolonged economic recessions, and the fragility of interstate relations. So, although it has been named for the next 10 years, but most of them which we are facing for today. So the type of challenge which we are facing in here, I mean, what we have been, at least I have been acknowledging, so these are not the type of solutions which we, I mean, which we have been already been experiencing in the past. So which means that these are much more complex, much more dynamic, and also changing quickly. So the type of solutions also which we need a kind of a new type of approach, and also the new technologies are needed. And one of the important potentials in terms of the digital technologies. And these are, again, a very recent kind of, document on year 2022 for different type of NGO organizations has been making a prediction what type of digital transformation will take us for today, and also the future, of course. And you can see, the AI and the cloud technologies, the cybersecurity, 5G plus and 6G in future. And also, moving on the list, also the high performance quantum computing. So you can see that, so these are, of course, we have been challenges, but at the meantime, different type of solutions, and most of the important solutions has been named by the digital transformation trends. And also, again, there's a report on the year 2021, and for the OECD, business at OECD, and from the business side, so what are the type of priorities on especially comparing the year 2020 and year 2021? And the number one has been named is the green transition. So this is a kind of an agenda for the business side. And the second one on the digital transformation and also the transition and infrastructure. And the third one on the human capital. But especially what I would like to emphasize on the change from the year 2020 and the year 2021. And the green transition is becoming very much important. You can see that change from year 2020 and 2021. So this also, I think quite clear that, especially after the pandemic, which we have been facing different type of challenges on the base of the climate change, and also the green development side. And the second one, of course, the digital transformation, keep it as important as in the same respect. And the third one, the human capital. And you can see also the change from year 2020 and also the year 2021 is the highest change in the human capital, so for the need for the human capital for the future. So therefore, this conference in this respect, I find it very, very important, because this type of challenges could be, named, addressed with the type of scientific solutions and technologies, but at the meantime also putting an efforts on this pre-conference and parallel events on developing the human capacity, especially our young scientists and students. And so also for the future on one of the important points on this twin green and digital transition, this is the agenda, and also the human capital. And from the moving to the topic of the conference, of course, we are talking about with the different points of the quantum technologies, materials and technologies, from fundamental physics to technological applications. And we have been seeing at the moment more potentials than before on the quantum technologies, and especially in terms of the type of applications from the, information technologies, medicine, environment, and energy technologies. But of course, we always, also has been addressed during the opening speech by our conference chair on Professor Ali Gencer, and also a contribution from the Switzerland that, and of course, the basic science is quite important. So therefore, to get more benefit to these challenges by means of the quantum technologies. So therefore, the more basic science is needed. And so this is a kind of spectrum on an overview of the current developments of the quantum science and technology for the year period of the 2018 and year 2022. So, I mean, the type of publications, what are the type of priorities or the keywords which has been addressed by the scientific community. So therefore, the more advanced on quantum technology, giving a contribution on the nanoelectronics, photonics, hybrid materials, and energy efficiency. So I don't want to, keeping to my time, that I don't want to go to detail, but these are all showing that the potentials and also the potentials for the collaboration areas. And in terms of also how we can see the quantum science and technology to achieve the sustainable development goal of SDGs of the UN. So, I mean, I have been put in the 17 UN SDG goals. And you can see that, I mean, directly 5 of the areas has been the quantum science and technologies can affect on these 5 areas, on the food and on the good health, and the water and the climate change and the energy, and also some others, but I mean at least that I have been just named shortly. And one of the important point, of course, I mean, it's clear, and also when I can see more than 300 participants in this conference coming from different type of areas on scientific backgrounds. So this is also a quantum science and technology, which we can see is covering to all disciplines. So this is also giving a potentials that there is much more need for interaction and collaboration, and more than the collaboration for the co-creation. And this is a kind of a change of the ecosystem, at least what we are trying to do in Turkey. I mean, we are trying to bring the knowledge creator and the knowledge user, technology developer and technology user into the same platform. So I think this, which we can see also the quantum area for the science and the technology parts, I think is a quite important area, which we are working very carefully on it. In Turkey. Of course, we have been funding the individual research projects, but we are putting more efforts also at the meantime that to form the platforms for the more than the cooperation, which we are aiming for the co-creation. And so the TÜBİTAK, I mean, especially for, I mean, nearly, I have been, I mean, named 300, about 300 international participants in the conference. So I am sure that you may know, I mean, a few, information, but I'll just say about who we are as TÜBİTAK. TÜBİTAK was founded in 1963. We have been just celebrated 59th year, and we are reaching the 60th year. We have been a kind of a agency. We are funding the universities, industry, fellows as an individuals in all, I mean, from bachelor graduates and also the postdocs. And also we are increasing science and society, science and technology awareness in the society. And of course, keeping the international collaboration on science, technology, innovation of Turkey. And also at the meantime, we are doing the research. Maybe this is a strange part, interesting part. I mean, we have been also doing with research. So altogether, we have been 6,000 personnel and more than 5,000 of them doing the research on different type of research institutes. And so this is our, I mean, in the left-hand side, you can see the priorities. So, I mean, they are aligning with, I mean, I think the global challenges and the global trends. On the right-hand side, I mean, which we are trying to, to develop a output and impact type of projects and platforms. And in this respect, we are trying to be emphasis on new knowledge creation models and also the human resources for co-creation to achieve the goals of our priorities. And this is, I mean, very crowded. I don't want to go to detail, but this is what it is showing that, I mean, which we have been putting a lot of different type of programs. And this type of programs we have been, while we are keeping funding the individual projects, but we are putting more efforts to form big platforms for technology platforms and also the technology development platforms and also the production development platforms. So on different type of areas, and of course the quantum is one of them. Especially now, one of the big platform is waiting on our list. Should be announced shortly. Will be funded by TÜBİTAK to start this year, hopefully. And also in the other side of the human resources side, on again, which we are trying to bring the fund our researchers, but also we are trying to attract the international researchers come to Turkey, continue their research in Turkey. And so these are the type of areas in terms of our forming the big platforms. So these are the different type of, and this is a kind of an areas which Turkey is putting itself to make it much more frontier. And some of the examples of these platforms are given in here, and which I think that they are also relevant to the quantum science and technologies and materials part. And I don't want to go to the details, but in here, so these are our technology platforms on health, energy, and materials. And in here, so different type of stakeholders, universities, state research institutes, and also the companies are coming together. And as TÜBİTAK is a funding agency side, we are not funding the individual projects, we are funding the platform, and the platform decides which projects should be funded. So it's a change of our mindset in here. So we have been more careful on type of outputs and impacts, but we have been, as I said, not individually funding the projects. We are funding the platform, and the funding decides which projects will be funded during at least 4 years' time. And also, as I said, while using this opportunity, I also, by means of yourself, including yourself and also your peer researchers, they also can come to continue their research in Turkey. So this is at the moment, we have been recently opened a program, and there are about 200 outstanding researchers are coming from around the globe. So you can see, and so they are coming, and then at least I give some examples in here, 5 of them, working on quantum technologies. And so they are coming from you can see from US, from Germany, from Czech Republic, and also from China. So they are all coming in here, continue their research for their certain period of the time, not maybe permanently. Of course, we have been very much willing to also invite for permanent positions, but at least to stay to 1 to 3 years period of time. And we are giving very good incentives to continue their research, not only by their own research, but also we are funding up to 5 PhD students for each researcher. And in terms of the international collaboration parts, and so you can see with these green areas, which we have already been collaborating, either bilaterally, which we prefer, or multilaterally. And one of from the multilateral part, Turkey is a full partner of the Horizon Europe program. So therefore, we have been also, collaborating with our, research organizations on research projects from academia and also industry side, by means of the Horizon Europe. And you can see at the moment, still we are just finished the first year on Horizon Europe, and the total number of projects and also the type of budget we have been directly received for our projects. So this is also giving our potential for further improvements. And in terms of, other than the funding part, a few last slides on what our capacity also in terms of our research institutes of TÜBİTAK. So one of institute on ULAKBİM, Turkish colleagues know very well. So we have been, the supercomputer of the Turkey has been coordinated by TÜBİTAK, and Turkey is by means of TÜBİTAK is a partner of one of the second high capacity supercomputer of Europe, together with the Spain, Portugal, Croatia, and it's based on Barcelona. And by using this one, of course, it's giving more potential for the quantum quantum side. And also with one of our research institutes on a BLGAM, based in nearby Istanbul, where I am now there, on quantum technologies, which we are working, in fact, more than 20 years in a period of time. And I just only give a few examples what we have been achieved and also what we are doing in here. So on develop and deploy one of the first quantum photonic random number generators, and this is already in use are in defense industry, and also the quantum key distribution system developed by circa 2000. So this is showing. And also at the moment, currently we are working with also with in European program with our European colleagues on photonic chips, especially for the quantum random number generator. And also we are working on a challenging project on the quantum sensors and quantum radars. So this is also potential, also showing that from all our colleagues that we are very pleased to collaborate also with our means of our partner, our research institutes. And we have one of the, also the important part is we have been one of the institute of the Basic Science Research Institute of TÜBİTAK. And by means of that, one of the top agenda on quantum. And we are not doing a research part, but especially we are bringing the researchers and especially the young researchers, students come to join us on this type of training programs. And you have been seen already been on the right-hand side on the course titles on by means of our summer schools or the seminars. And I know that some of our colleagues who are the partner of the associate member of our institute are attending this conference as well, and they are also contributing. But this is more increasing the awareness and also the type of a collaboration and co-creation between the researchers in Turkey. And finally, once more, also thank you, giving an opportunity for me to be joining at least by online what we are doing and how we are, observing the changes and potentials and what we are doing and also what we can offering. So during this conference, enjoy the fruitful, meetings, and we are also learning by means of my colleagues, and they will report me. And we are ready more cooperation and collaboration in for the future, and enjoy also your stay in one of the good part of Turkey at Bodrum, and nice conference and fruitful discussions. Thank you very much.
Professor Hasan Bandal, thank you very much for your time and for giving us this clear talk in this opportunity. If there is any question or comment in the audience? No, I think we thank you very much for your time and for such a nice presentation. Thank you.
I thank you as well. Thank you very much.
So we start now with the next presentation from our distinguished Professor Valery Vinokur, who will talk about the ferroelectric topological routes for nanoelectronics, negative capacitance, and more.
Thank you, Ali. Does it work? Yeah. Looks like. Okay. First of all, I would like to thank here. Okay. Yeah. Ali and all the organizers for having me here. It's a great honor, and it's not like, okay, the first conference organized by Ali, and all of them are absolutely excellent in every respect. So thanks again. And, well, let's start. Okay, this is, okay, Chicago Bodrum, our connection. You can immediately recognize. And those are collaborations. And I'm going to touch actually a little bit more than it was planned in the beginning, not only ferroelectrics, but also a little bit of superconductivity. So we have the full list of our collaborators. And let's get started. Well, okay, not the right direction. Okay, first the dedication. Okay, I cannot, my French is more than rusty, so I wouldn't risk to pronounce this quotation from, Marcel Proust in French. And it says the tail wedge of discovery consists not in seeking new landscapes, but in having new eyes. And this is... Okay, you just, because I can't control it, and I don't know how well I'm heard. Okay, so the last century, it was actually the time of what is called topological revolution. And basically it was this fundamental work by these three people, Vadim Berezinsky, David Taulis, and Michael Kosterlitz. Two of them got Nobel Prize for their discovery. Oh, thanks. And unfortunately, Vadim Berezinsky didn't live long enough to get it. And this was indeed the revolution, because before, well, it was another great discovery, basically, Landau's discovery of one, which is considered one of the most fundamental in condensed matter physics, the possibility of the spontaneous symmetry breaking and phase transitions, this theory of second order phase transition, which is just the symmetry breaking. And then, but since then, it was believed that actually every state of matter should have what is called order parameter, and other states of matter just do not exist. And one of the achievements of this Berezinsky, Kosterlitz, Taulis new kind of phase transition was the finding that there are actually states of matter which are not characterized by any order parameter, but are characterized by topological order. And what we're going to do, actually, we're going to combine these two things today in what we're going to talk about. And this is basically the contribution, so this is symmetry and topology, and there is a contribution of two great minds again of 20th century, Amy Noether, who actually put the foundation of all the contemporary physics. Actually, we start our study of physics from what she created, because her achievement, which is called Noether theorem, is that if the system has some symmetry, then there is some conservation law corresponding to this symmetry. And Vladimir Arnold formulated one of the deepest theorems in the topology of the 20th century, and this is exactly Arnold's theorem. Sometimes they refer to this as Kolmogorov-Arnold-Moser theorem, which we're going to explore during our presentation all the time. Well, those are just beautiful examples of what we call symmetry. We know this pretty well. And this can be considered as topology. We can see vortices in one of the great paintings, and vortices is just the topological excitation. Okay, now, what is Arnold's theorem? Okay, we'll just talk about this a little bit later, but the statement is extremely simple. Suppose that we have incompressible liquid, for example, and this incompressible liquid is sort of confined in a finite volume. And then Arnold have shown that only two configurations for this liquid flow is possible. One of them is very familiar to everybody who is doing superconductivity or hydrodynamics, which are just vortices. But there is another, a little bit more exotic configuration of this liquid, which is sort of like self-linked, and which is called Hopf vibration, or simply Hopf. Why this is interesting? Why it's not just the mathematical construction? Well, there is another thing which we all know, but we all miss in a beautiful Feynman textbook on statistical mechanics. There is a small chapter, and when we are students, we are really lazy to read it, which is called Another View, or Another View on Superconductivity, and where Feynman formulated that basically superconductivity can be very well described by hydrodynamics of the superconducting condensate, and that this liquid is basically this incompressible liquid, and then it means that this Arnold's theorem applies to every superconductor. And what does it mean? Well, immediately if we introduce the gauge field theory to describe these topological things, it immediately means that our Hopfion is nothing but very well-known Bohm-Kasher interactions between electrons and, let's say, vortices for the moment. And why this interaction is so important? Because this is a really long-range interaction. So I remind, what is this about? We know pretty well what is Aharonov-Bohm effect, meaning that if we take, for example, electron around some magnetic flux, then the phase of the wave function acquires some phase, and then, and this doesn't depend on the distance. This doesn't depend on how large is the radius of this circle. And then one can construct a gauge theory for superconductors, and we'll talk about it in a minute. A new kind of superconductivity can appear. Well, first of all, this kind of constructions describes all the existing superconductivity very well, and the phenomena which were not possible to describe before. For example, with this gauge theory, it is possible to construct a theory of the superconductor insulated transition. Beautiful experimental fact. Until recently, no theory did exist. And another thing, which we are going, also to talk a little bit more, that these topological excitations, Hopfions, actually appear in ferroelectric nanoparticles and give rise to some beautiful properties of them. So let's start a few words about superconductivity. So to construct the theory, what we have to do is to just, to draw actually the world lines for vortices, or for magnetic charges, and for the usual charges. And then we can immediately write down these Aharonov-Bohm-Kasher interactions and write this, what is called, the action, Aharonov-Bohm-Kasher action, which immediately takes into account all these topological excitations. And as a next step, this action is called Chern-Simons action, and it quantifies, the field theory for this infinite range Aharonov-Bohm-Kasher interaction. And as a next step, we can use symmetry consideration against, this is a textbook exercise, we can write down into the action all the terms which are required by the symmetry, and what we can compose the action, and we can introduce gauge fields which make our all interactions local, as they should be, because we don't want them to go instantaneously on the infinite distance. So we have the usual kinetic terms in our action, then we have our Chern-Simons topological terms there, and this action immediately describes, for example, superconductor insulated transition. Actually, it can describe the GIF, sort of like phenomenological theory on the Ginzburg-Landau level of high temperature superconductivity, and explain why these high temperature superconductors do exist and have this high temperature. This we were discussing some other time. And now move on. And what I would like to say is that as soon as we construct the theory of the superconductor insulated transition, we immediately see that there are three phases which do exist in the vicinity of this transition. One of them, of course, is superconductor. Another is a new phase, and it will be it will be Carla Trugenberger, who will be giving a talk, which I invite you to attend, where a theory of superinsulator and related phenomena will be constructed. And then, if we analyze a little bit what happens because of this long-range Aronov-Bohm-Kasher interactions, we will see that if we have special superconductor, which has in a normal state large dielectric permittivity, we will see that we get superconductivity of completely new kind. The usual superconductivity is described, as you know very well, very successfully by Ginzburg-Landau equation, which is by definition local equation, and in which, all the superconductivity effects, Meissner effect, which is like the basic property of superconductivity, in terms of field theory is called Anderson-Higgs mechanism, and it means that our electromagnetic field acquires, or gauge fields acquire a mass. If we analyze what happens in a superconductor, which stems from a metal which is in a normal size, normal state, has a high dielectric permittivity, we'll find out immediately that this Ginzburg-Landau approach doesn't work. Ginzburg-Landau functional becomes non-local because of this long-range interactions. It doesn't apply. We cannot describe the superconductivity with Ginzburg-Landau equation. I repeat it again. And this is new kind of superconductivity which appears, which we called, well, we couldn't invent better name, but type 3 superconductivity. Christina, who is here, will be giving a talk on it. And this is new kind of superconductivity, completely new. For example, in this kind of superconductors, usual Abrikosov vortices do not exist. Just one of the features of these new superconductors. So I invite you to attend Christina's talk. And we now move on from superconductivity to ferroelectrics. But before that, I have to mention that this kind of new superconductors, they have inherently granular structure. And this granular structure occurs because the system remembers that it has superconductor insulated transition, and then in the vicinity of this transition, every superconductor has granular structure. It's like superconducting droplets which are connected by the tunneling Josephson junction. So again, Christina is going to talk about it in a much more detail. Please come. Now, okay. Topological materials is quite, let's say, fancy name. A lot of things which we call topological materials, and one can immediately ask if ferroelectrics do belong to the same class of topological materials, and if so, what is so topological about them? Well, we know pretty well what is ferroelectric. It's just like, to entertain you, because you know this better than me, is the same as ferromagnet. It's just the material which has spontaneous electric moment, and it's characterized by spontaneous polarization there because of its construction. And yes, there are a lot of publications in which topological excitations in ferroelectrics have been seen. They carry different names. Well, vortices, of course, they have been seen. There are skyrmions, beautiful topological configuration. But basically, it can be, well, we're not going to talk about this today, but basically all these configurations are reduced to two of them, according to Arnold's theorem, Hopfians and vortices. All the rest are one or another modification of this basic two. And, well, why they are so interesting? Because they split into the domains, and these domains, well, they follow exactly this Landau-Lifshitz-Kittel domains theory, and okay, these domains describe their beautiful properties, and this can be described by usual Ginzburg-Landau functional, which is in connection with ferroelectrics. It's called Ginzburg-Landau-Devonshire functional. So everything is quite obvious. One thing can be immediately noticed, that if we have ferroelectric nanoparticle, and then polarization is trying to be tangent to the surface confining this nanoparticle, because then there are no charges and this minimizes the energy. And then there is immediate analogy between the hydrodynamics of incompressible liquid and the physics of ferroelectricity in ferroelectrics. And then it means that this Arnold's theorem now, okay, don't bother reading it. It's just whatever. It's just this, this famous theorem from this famous book. This is Vladimir Arnold, saying that in this mathematical language that there are only two topological excitations that can exist in the confined volume, and then that because of this self-linking, it should be finite knotting or helicity in this Hopfian formation. And this is basically the illustration of this notion once again. So if we start introducing or polarize our ferroelectric nanoparticles, only two topological excitations are possible, vortices, Hopfian, and of course this nanoparticle can split into the cells. Each of them is carrying each of these topological excitations. Well, this is just the illustration we have. Yes, okay, these illustrations, well, it's not a real experiment, unfortunately, yet, or not made to this extent, but those are numerical simulations. Numerical simulations of a ferroelectric nanoparticle in which we can have, if we use the parameters of one of the most, let's say, technologically used one, and we found that it forms different topological configurations. So this is just, okay, a vortex made by the polarization lines. Then if we increase, actually, applied electric field, we can really form a Hopfian within this nanoparticle. Okay, this is just the illustration of this Hopfian, which has, okay, at the pole, it has like the vortex, exactly in okay, according to this Arnold's theorem. So here is the place for the Hopfian, and this is the cell or part of this nanoparticle which carries vortices, and Hopfian has non-zero chirality. This is another illustration of this Hopfian-like structure in a nanoparticle, just numerical simulations. And please note what is the size of this nanoparticle which we simulated. It's like about 20 nanometers, so small enough and so good for microelectronics. We're not going to discuss all the things where these topological configurations and the related structure can be used. But what we're going to discuss in detail is the negative capacitance. This is time remaining, okay. 2 minutes, okay, the time is running fast. Okay, so I'm trying to run fast quickly about this. So why these Hopf ferns are interesting? Because they can show that in ferroelectric nanoparticle, negative capacitance can exist. Okay, let's skip this, since I don't have time, and go to the technological issues. Basically, why are we interested in this like negative capacitance? Okay, for two reasons. Now microelectronics reached the limit where the consumed power does not allow this microelectronics to be efficient anymore and to pack more, let's say, field effect transistors into the microchip. If we can decrease the consumed power, then we can make the new kind of the chips, and this will be the revolution in the microelectronics. Now, we know pretty well from the school course that negative capacitance cannot exist. This is like the law of energy conservation. And nevertheless, we have shown that it can very well exist. And if we take the small nanoparticle, let's go to it. If we take small nanoparticle about the size of like 20 nanometers, we can find out that this nanoparticle is split in exactly 2 domains. And if we make this nanoparticle in a disk shape, then it means that if we apply the charge to the plate, then in order to compensate this charge, this domain wall should move. And since it moves, its length becomes smaller, and the area. It means that it decreases this surface energy. And then it means that actually it overshoots, because it would love to move a little bit more than it's obliged due to electrostatic effects. And if it moves a little bit more, then the electric field which appears there overcompensates the electric field due to applied charges, and it means that we have negative capacitance in our nanoparticle. As simple as that. Now, the time is over, right? I believe.
No, I misunderstood the hand signal.
Huh?
I misunderstood some hand signals, so you still have some time.
How much?
15 minutes.
Oh, 15 minutes. Good.
Yeah, I misunderstood.
Okay, then let's come back. If I have 15 minutes, it's like a slightly different story. Okay, so what can we make out of this negative capacitance I was talking about? Okay, first thing, of course, the conservation of energy is the thing which we cannot violate, and the thing about this negative capacitance in itself, in a one capacitor cannot exist. Okay, it can be created, but it's not going to be stable. So what we have to do, if we want to make this field effect transistor, basically what you see on this picture is the field effect transistor. We have, then we have a combination of 2 of them. Let's say this negative capacitance, this one with the ferroelectric, divided in 2 domains, and then another one. Together, the full capacitance is positive, but it can be as small as, very small, the total capacitance, close to 0, and it means that actually electric fields and voltage by which this field effect transistor operates can be done about 100 or even 1,000 times smaller than what we have now. It means just reduced heat, and it means that new kind of microelectronics, which can be at least 100 times more efficient, can be constructed. Now, This is just like, okay, the device which we propose. So this is just capacitor with the ferroelectric inside, 20 nanometers in diameter, divided into 2 domains. Now, is it good enough? Not quite, because like, okay, we can analyze it work a little bit and find out that basically once we've done it, its parameters are completely fixed, and it's not like, okay, because all the sizes are predefined, we cannot vary much its characteristics of this transistor. But what we can immediately do, we can make immediately a little bit more complicated device. We can code this ferroelectric with the usual dielectric one, then the effective circuit is like that. And well, it's a little bit boring analysis, but it's on like, I don't know, first year student available, that if we actually change the size of this, our dielectric coating, we can change the characteristics of our field effect transistor as much as we wish. We can achieve, okay, all these like possible best characteristics. Okay, let me find where it is. Okay, actually it's here. So depending on the size of this coating, we can be in a different regions, and there are 2 critical sizes of this coating for like this ferroelectric size of 20 nanometers. And if the coating is between these 2 critical sizes, then the capacitance of this gate on the, excuse me, of this field effect transistor is negative, and then its characteristic can vary with the size as much as we wish. Now, those are these, okay, characteristics, which is dependence of this drain current, which goes through this, like, okay, let's see. Okay, so drain current, this is field effect transistor, the usual construction, though, so one plate, another metallic plate, this is capacitor, this is dielectric, which protect our semiconductor where we have this like source and drain parts, which protects it, okay, from leaking electricity from this capacitor. And we can find this like IV curves, so to say, and then we can choose changing the size of our dielectric coating. We can find the best characteristics of our field effect transistor, and okay, so that on one hand, its characteristics are good enough, and on the other hand, it's stable, meaning its performance is stable. So then, for every given material, we can find the optimal size of the coating, which provides the best performance of the field effect transistor. So this is what we're going to do. And then there is one more beautiful effect, which comes from the negative capacitance and this construction of the ferroelectric, mainly. If we find out what like is the frequency of oscillations of this domain wall, and especially when we have this like, okay, negative capacitance, we find out that it's sub-terahertz or terahertz region, which is quite convenient for application because, you know, I mean, you can find any release or any review and find that basically what our modern technology is going to die without are these beautiful and small terahertz sources and terahertz like, okay, devices. Because our usual terahertz devices have the size, okay, I don't want it to be like, okay, much too critical, but they're not small. And this what makes, okay, their technological use for the moment impossible. One of the best technological use for, and with this, the size of this terahertz source, for example, can be scaled down to just 20 or 30 nanometers. So it's really microelectronics capable to work in a terahertz or sub-terahertz spectral band. And well, those are just characteristics of how we can calculate them, the characteristic of this, our thing. And basically this terahertz or sub-terahertz radiation has been found experimentally. We described like how many years now? About 4 years ago. What happens if we have this like ferroelectric films split into domains, and what kind of frequency behavior we can expect. And last year, the paper in Nature was published when they have seen exactly what we have predicted before, for that. Well, and this just, to finish the story, those are, this is like possible technological use for these our terahertz devices. Well, I missed probably the most interesting and the most important one here. This is for medical diagnostics. Since terahertz radiation is not as damaging as X-rays, on the other hand, and on the other hand, is very penetrating. I mean, because of the wavelengths into the biological media. This is absolutely irreplaceable tool for the medical diagnostics. It can, for the early diagnostics of the things from heart diseases, cancer, any damage of the, biological tissues, and so the demand is going to be extremely high. And another thing which I didn't put here is pharmaceutic. Again, because it's not X-rays, it's not damaging these organic molecules. So again, it's not my invention. I was reading this in one of the press releases that that it's going to be irreplaceable for pharmaceutic and composing new kind of medicine and control the composition and organization of the biological molecules which are the part of the medicine. And actually this is the end of the story. Maybe one more thing to tell, because China was somehow mentioned in one of these introductory talks. And I remember I was reading one of the press releases. They didn't say exactly, it was said that it's negative capacitance, which is interesting. And this press release was saying that Chinese government waived all the taxes from all the companies and all the scientific institutions which investigate negative capacitance. So it means that they understand pretty well how important for the electronics this negative capacitance may be. So we came to the end. So this is conclusions. So basically this negative capacitance is a domain-provided effect. And it's again very interesting because it was Rolf Landauer who first indicated that negative capacitance is possible. Then it was a lot of publications and a lot of patents in which this negative capacitance was used. And it gave me a beautiful feeling reading these patents. Because, imagine that you are reading the patent about what? Some robot doing the homework and cleaning your house. You read the patent, you see the technical drawing, and you see one black box there which says time machine. The part of this robot is time machine. Of course, you understand immediately that this kind of robot can be extremely, extremely efficient with a time machine. The only small detail not of one of okay. And then imagine that this patent doesn't tell how to make this time machine. So there are a lot of patents about all this like possible microchips which says, okay, and this is negative capacitance. You will never find how to make this negative capacitance. Now, all of us, we know how to make it. And, well, so our finding says that it's exactly two-domain ferroelectric which provides this negative capacitance, which immediately gives the characteristic size for all these industry-used ferroelectrics between 5 and 20 nanometers, and then negative capacitance-based resonators open actually new route and new area for this, okay, new kind of technological devices. Well, not the advantage that they're small. They consume about 100 or 1,000 times less power than the usual one, because basically what is happening there, instead of usual LC circuit, for which we may have the resonance, we have negative capacitance, positive capacitance line, and it means that the power which is consumed there is like 1,000 times less because it's not the inductance there. Okay, then I think I'm done. Thank you for your attention.
Thank you, Valerie, for a very interesting talk. And we have about 4 or 5 minutes for questions. Yes?
You said that in ferroelectric substances, you could have negative capacitance and you can make a generator of terahertz frequencies based on this resonance. My question is, what determines the frequency of this resonance? Frequency of the resonance, what determines the frequency? Can you tune this frequency, and what is the line width of the resonance?
Okay. The frequency is like, okay, comes from the frequency of the oscillations of the domain wall. Just, if you take just the usual ferroelectric, which is like PTO or something like that, you will immediately find that if you have this, okay, multi-domain structure, it will be in a terahertz region. You can tune it, okay, you cannot tune it 10 times, but you can tune it a little bit, changing just the sizes of your ferroelectric nanoparticle in which it is there, and changing a little bit changing the number of the layers there.
And what is the line width? You see, the problem with terahertz generators is that usually the terahertz generators are pulsed and they generate continuum. So it's not a monochromatic terahertz frequency, and that's a main problem. I mean, people suggest to use antiferromagnets, but antiferromagnets, they also have pretty wide band. And my question is whether you can overcome that in this case and create really monochromatic terahertz frequency generator.
Okay, excellent question, thank you. Basically, okay, we're doing, okay, calculations and simulations. The preliminary answer is yes. That's why, I mean, that's why it is so interesting, because it doesn't work the same way as like, okay, antiferromagnetic resonance, because this okay, motion of this domain wall, in a sense, is very well controlled. I mean, not by us, self-controlled by the ferroelectric construction.
Thank you.
But thanks for this question, and that's why we really look at it as the very perspective direction.
So do we have another question? So maybe I'll follow up on that, because I was also curious about this terahertz generation. I don't quite, so just by putting a field on this weird new capacitor that, I don't know if anyone's built it yet, you will generate terahertz, and it can also be used as a detector. So it has some things in common with Josephson junctions then.
No, it's not the Josephson junction.
No, but I
because-
mean the fact that it can be used as a detector and a generator of the radiation, of terahertz radiation. Right?
Didn't quite get, Laura.
Oh, because the Josephson junction can generate microwaves as well as detect microwaves. And so my comparison is that this device, if we could build it, would be used both for generating terahertz and for detecting terahertz. Is that correct?
Yeah, absolutely. Yes, so we can make, both of them. That's why one of the applications is, use it for the next generation of our iPhones when we make them, or for space communications where terahertz is preferable, or for example for filtering. This is exactly, to filter, this was the question of how we can make this monochromatic one. Just the use, terahertz source, and then terahertz filtering, which make, really,
So
narrow band.
what would be the main roadblocks in building something like that?
Well, it's it's another question, and since we are not only physics but technology as well, basically what we are looking at, and let's put it that way. Now, as many of you know, I am not working for Argonne National Laboratory anymore. I am working for the company, and this is exactly what we are looking for. We are looking for another company or foundry which will be producing these ferroelectrics for us and for other technology. And as many of you know, with the foundry, the negotiations are very simple and straightforward. If we are going to order a chip which will have 10,000 these field effect transistors with the ferroelectric, they are going to do it like that for tomorrow. When they tell them, please make one, they say,
Okay. So before we thank you again, what I'd like to do is present you with a certificate. Thanking you from the conference.
Thank you so much. Thank you, Laura.
Thank you very much.
Hoş geldiniz.
Dear guests, distinguished scientists, first of all, welcome to this beautiful city.
Kendimi tanıtarak başlayayım isterseniz. Çok uzun konuşmayacağım ben. İsmim Mustafa Ünver Böke. Milas Kaymakamı olarak görev yapıyorum ve yaklaşık 1,5 yıldır Milas'tayım. Fakat 17 yıldan fazla, 18 yıldır kaymakam olarak görev yapmaktayım.
I have been a local governor for the last 17 years, but I've been Milas governor for the last 1.5 years.
İşim gereği çok programa katılıyorum ve çok konferans ve programda konuşma da yapıyorum. Ancak bugünkü konuşma benim için çok özel çünkü birbirinden değerli bilim insanlarına hitap ediyorum. Dolayısıyla kısmen hatta oldukça heyecanlıyım.
I take part in many conferences and gatherings, doing opening speeches, but this one especially excites me because I am addressing distinguished scientists from all over the world.
Programı haber aldığımda özellikle katılmayı arzu ettim. Açılış kısmına yetişemedim fakat şu anda buradayım. Bunun temelde iki sebebi var. Bir tanesi değerli hocamın nazik davetleri. Bir diğeri özellikle son birkaç yıldır özellikle fiziğe ve kuantum fiziğine duyduğum ilgi.
I was really excited when I received the invitation from my distinguished friend. One of the reasons is that because I have a special interest in quantum physics, and this is one of the main reasons that I am really excited to be here. I'm sorry that I couldn't make it to the opening ceremony because I was held up by other activities.
Akademik olarak bir sosyal bilimler öğrencisiydim. Sosyal bilimler mezunuyum. Yüksek lisansımı da İngiltere'de yine sosyal bilimler ana bilim dalında vatandaşlık ve demokrasi alanında yaptım. Ancak az önce değerli hocama da kapıda söyledim. En büyük idollerinden biri Richard Feynman olan bir sosyal bilimler mezunuyum ben. Eğer filmi tekrar geriye sarma, hayatımda bir yaklaşık 25 yıl geri gitme imkanım olsaydı kesinlikle fizik alanında akademik çalışmalara devam etmeyi isterdim.
I'm a social science graduate, and I did my MSc in social sciences in England on citizenship and democracy. However, if I was able to take time back 25 years, I'm sure I would have been a physicist, because I especially admire Richard Feynman, and he's one of my idols.
Dolayısıyla bugün burada ne kadar heyecanlı olduğumu anladığınızı umuyorum. Bu heyecanın geçtiğini umuyorum. Ben bu çalışma süresince ve çalışma sonunda oluşacak enerjinin, sinerjinin güzel başka çalışmalara sebep olması, neden olmasını diliyorum. Bu arada çok kısa bir bilgi vermek isterim. İlçemle ilgili, görev yaptığım ilçe şu anda üzerinde bu tesisin de üzerinde bulunduğu Milas ilçesiyle ilgili. Milas ilçesi tarihi bin yıllar öncesine dayanan, üzerinde pek çok medeniyetin hayat bulduğu, medeniyetlere başkentlik yapmış nadide şehirlerden bir tanesi.
I hope that this conference will lead to a good synergy, new science and new technology. In the meantime, let me give you some information on Milas, where you are located at the moment. Milas has a history of thousands of years of history. Has been a capital of many civilizations throughout the history, and it is one of the beautiful corners of the country too.
Özellikle antik kentlerin ziyarete açık olan antik kentlere, bilmiyorum böyle bir program var mı? Eğer yoksa ben teklif ediyorum. Evet, bunu hem Milas Müzesi'ni hem antik kentleri hocam mutlaka gezmeliyiz bence. Bunun yanında yine yüzyıllardır zeytin ve zeytinyağı üretiminde çok önemli bir noktada ve Avrupa Birliği'nin coğrafi işaretine sahip Türkiye'nin tek zeytinyağı, Milas zeytinyağında mutlaka tadına bakmanızı tavsiye ediyorum.
I strongly suggest that you go and see some of the antique cities located around. Milas Museum is especially one to see. And also, Milas has been home to olive and olive oil for hundreds of years, and it has one of the European Union certificates. And I strongly suggest you try and at least get a sample of Milas olive oil when you go back.
Tekrar tüm katılımcılara selam ve saygılarımı sunuyorum, başarı dileklerimle.
I again offer my deepest respects to all participants, and thank you for participating and coming to Milas.
Our district governor will be around. Hopefully, when he makes another chance, maybe he will attend one of the social programs at this hotel. Hopefully tomorrow or the other day, anytime when he is free with his wife. So, yes. And so, Laura, chair is yours. Okay. Okay.
Well, I recommend that we, first of all, thank our speakers, all of our speakers again, and thank the governor for showing up. And if anybody's not opposed to it, I propose that we do take a 15-minute break, and we come back at 1:45, okay? So see you in 15 minutes.
He is from the National University of Singapore, and he will talk about strong spin lifetime on isotropy in ultra-thin black phosphors. I welcome him to the stage, please. Your microphone is open?
This one is not. Or
On?
okay. I think, yeah, now it's perfect. So thank you so much. And before starting my talk, I would like to thank Prof. Ali Gencer and Mr. Serdar Öncül as well for helping a lot before I came here. So I'm Ahmet Avşar. I'm assistant professor at National University of Singapore in the Department of Material Science and Engineering. And I'm a NRF fellow. Indeed, I just joined like 3 weeks ago, and before that I was in the UK at Newcastle University. So my talk will be slightly different. It will be more focusing on the material science aspect, and I will be introducing you to a material called black phosphorus, which is like in the form of two-dimensional material, and I will be discussing why it's quite interesting for spintronics research. So last 5-6 years we have been working heavily on this material, and now we have quite well understanding of how the spins are propagating in this material. And as you can already see in these schematics, the material is not a typical flat material, so it has this pucker structure with very well-defined armchair and zigzag edges. And I will be showing you that, first of all, the material, it can sustain, it supports the spin transport very well. It's two-dimensional. You can apply gate voltage to manipulate the spin currents. And also, since the material is highly anisotropic, I will show you that also spintronics properties are also highly anisotropic. So this is a slide that you might have seen already. So this is how the model heat flux is increasing over the years with the CMOS technology, and indeed it's a bit worrying because, for example, here you can see an image from a mobile phone processors which is discussing that their processors are melting butter less than the other competitors. But it's a serious problem that you might even feel in your pockets with your mobile phones. But this is a problem that we are already quite familiar. In the past, we had this bipolar technology. It was going through the same issue, and by just changing the technology from bipolar to the CMOS, we gained around 10 years. So the question that we have is, what's beyond CMOS here? So it cannot keep continuing like this. So there are different approaches. Either we will be using completely new materials, or we should go beyond charge-based approaches. So my research is focusing on this beyond CMOS area. We have different research focuses. For example, we are mostly working with the two-dimensional materials, and we are doing some devices by utilizing the interlayeric stones, or we are utilizing the spin to carry and also process the information, or we are also using some novel materials, mostly atomically thin materials, for this beyond CMOS technology. So today I will be discussing about the spin transport aspect of our research, and mostly I will be focusing on a material called black phosphorus. So I'm sure many of the audience is already quite familiar with this concept of the spintronics. So it's very similar to the electronics, but here, basically, rather than dealing with the charge degree of freedom, charge property of the electrons, we are focusing on their angular momentum property, which is called spin. It has been for a long time considered as complementing or even replacing the charge degree of freedom in the logic devices. And there have been lots of proposals which are just utilizing this spin degree of freedom for faster and also low power devices. So this field, it got Nobel Prize in 2007 to Albert Fert and Peter Grunberg because of the GMR effect. But if you would look at the dates for these proposals, you will see that most of them are quite old, and they have not been experimentally realized yet. And one of the main reasons for that is we have some basic requirements with the materials. So we need some materials which can support this kind of devices that are aiming to utilize spin degree of freedom. So today I will be most talking about the spin channel material aspect of such devices. In terms of the material, we are highly interested into the two-dimensional materials, and towards the end I hope you will be convinced that these material systems are quite promising for spintronics. But everything started with the isolation of monolayer graphene through a bulky graphite crystal by a group of Manchester, which got later on, again, also a Nobel Prize for the discovery. So these are just atomic, but this is like monolayer carbons packed in the hexagonal structure, and it's quite promising for electronics, etc., including also the spintronics. So the field started with the discovery of the graphene, but now we have hundreds of isolated monolayer materials, and some of them particularly I like it, and we also have contributed in their discoveries. So these are particularly interesting for spintronics research. So what we are trying to do is like combining basically the spintronics with the two-dimensional materials for mostly fundamental research, but by keeping an eye on the applied research as well. So what I will be talking today is mostly this black phosphorus as a spin channel material. So the idea is we should be able to induce some spin accumulation in a non-magnetic material, and these spins, they shouldn't die in short time, so they should be living longer so that you can do some device operations for this beyond CMOS era that I have been discussing. Okay, so this is my outline. I will be giving a brief introduction to what has been done with the spin transport in conventional materials or also graphene. And then later on I will be discussing why black phosphorus spin transport is special. And then I will be also discussing the effect of the crystal anisotropy, the crystal structure, and also the effect of the charge carrier concentration or charge carrier types on the spin transport will be also discussed. So before showing you lots of data, I wanted to give like very brief introduction, the measurements that, the typical measurements we are doing. So I will be trying to be less boring, but these are required to be able to really understand the rest of the talk. So this is a measurement called non-local spin valve. So basically you have 4 electrodes, and then on the right side you are just deriving the charge current, but there is no charge current propagation at the other side of the circuit, and then you are creating some spin accumulation by passing the current through a ferromagnet. And these spins, of course, they are diffusing to the right side, but they're also to the left side. And if you can place your ferromagnetic detector in a length shorter than your spinel excitation length, you should be able to measure some signal which is directly coming from the spin diffusion. And this is a very typical spin valve measurement that you will get if you measure any materials under this non-local spin valve geometry. I'm showing it because later on I will be showing you that these kind of measurements are giving different response for black phosphorus, and I will try to explain why they are different. The second measurement we are doing is called Hanley spin precession measurement. So you again do the same measurement, you have now the spins pointing in plane, and then you start to apply very low magnetic field. And then this spin, they start to precess within the plane. And depending on the direction of this spin with respect to the detector electrodes polarization, you get this kind of Hanle spin precession curves. So by doing some fitting, you can get an idea about the spin lifetime and spin relaxation time, and also spin diffusion constant, which would give like a parameter called spin relaxation length. And the third measurement one can do is the following. So in the Hanle curves, I mentioned that you are just applying a small magnetic field, and that's sufficient enough to do the precession. But what would happen if you apply much higher fields? So in that case, your ferromagnets, which are polarized along the in-plane, you are forcing them to be out of plane. So both ferromagnets are now out of plane. The spins that you are introducing into the channel, they are also pointing out of plane. And this is a bit different measurement than the other ones, because in the previous ones, the spins were just lying within the plane. So now you are forcing to be the out of plane. And this is the typical signal that you would get. This is the Hanle spin precession measurement that I have mentioned at the low field regime. And whenever you are applying, whenever you are forcing these ferromagnets to be out of plane, then you are forcing the spins in your channel to be out of plane. And by comparing the magnitude of this signal and this signal, you can get an idea about the spin anisotropy, meaning that what's the spin lifetimes for spins pointing out of plane versus spins pointing to the in-plane. Of course, before two-dimensional materials, the spin transport was already extensively studied with the conventional materials. For example, there was quite nice efforts with the spin transport with the metals, and the materials like aluminum, copper, silver were shown to be exhibiting nice spin transport measurements. So here there are some advantages and disadvantages of the metal spintronics. So the good thing is it works at room temperature, but the issue is the magnitude of this spin signal is extremely small, so you cannot really do so much device operations. And also spin relaxation lengths are generally very short. Yeah, so there was a paper which was discussing that if you can improve the interface quality in the devices, then you can increase the spin injection efficiency. Therefore, you could make the spin transport much better. But still, the signals are quite low for the metals. Spin transport in semiconductors was also studied very extensively, and especially with the silicon, gallium arsenide, and germanium. And the results were quite promising. They are working excellent at low temperatures. So, but whenever you were going above 80 Kelvin, the spin transport was generally dying in these materials. But recently there have been also a group, there is another group as well, showing that in silicon you can still get the room temperature spin transport by, again, improving the contact resistance. So the all hype with the two-dimensional materials was the following. So we were predicting that because the material has high mobility and it's made of the carbon atoms, which are quite light atoms. Basically, you would expect very low spin-orbit coupling strength and no hyperfine interaction. So we were expecting that we will be inheriting the advantage of both metals and semiconductors. And the first devices were successful. So a group in Netherlands, Bart van West group, has demonstrated that the spin transport works up to room temperature with relaxation lengths above micron. And so those results were good, but indeed it's still, it was like 3 orders of magnitude smaller than the theoretical expectations. So the field has been pushing the efforts much more, and for example, it's now shown that the spin relaxation length in graphene at room temperature can exceed like 30 micron, which is highest ever measured in any material systems. And this can be also realized in the large-scale graphene, and a group in in Sweden, they have already demonstrated that you can make some basic spin circuits by using graphene. But there is one major problem with the graphene. So not only for spintronics, also for electronics, etc. These materials is a semi-metal, meaning that it doesn't have any band gap. And therefore, you cannot really turn on and off the conductance in this material. And the main interest with the two-dimensional spintronics is coming from the gate tunability. Therefore, you really cannot do much in terms of using its advantages for being an atomically thin material. So we try to solve this problem by using a bilayer graphene, and in bilayer graphene, whenever you apply some vertical electric field, you can induce some band gap, and we have shown that as you are opening the band gap, you can also control the spin propagation within the material. But there is still lots of issues that it only works at very low temperatures. So what we were looking was a two-dimensional material which has a sizable band gap and which can also host the spin transport very well. So that's how we started with the black phosphorus. So before showing you anything about the spin transport with the black phosphorus, let me just put some example measurements obtained in graphene spin valves. So this is like typical spin valve geometry. You have this rectangular type spin valve signal. This is the Hanley spin precession measurement. So the amount of the signal that you have is exactly the same with the spin valve geometry. And also the anisotropy in this material for spins out of plane versus in plane is very isotropic, meaning that the spin life, it doesn't matter if the spins are pointing out of plane or in plane, they have the same lifetimes. And I will show you that the black phosphorus is different, but let me just introduce very briefly about these materials. So this black phosphorus crystal structure, basically it has this pocket structure with some edges are terminated with the armchair direction and some edges are terminated with the zigzag direction. And this material has layer-dependent band gap. In this case, it has a band gap around 0.3 eV in bulk, and whenever you go to the monolayer, the band gap becomes 2.1 eV. So it's a nice semiconductor compared to the graphene. But typically, you would expect quite low mobility for semiconductors compared to the graphene, of course. But the mobilities that we are measuring in black phosphorus is quite high. Indeed, it's even approaching 50,000 cm squared per volt per second at low temperature. So this also makes this material quite interesting for us. And there have been like some studies showing that if you would be sending the charge current from here to here, or versus here to the other edge, the mobility of the devices are changing. So because it's a highly anisotropic material and the charge transport, later on it was shown that optical properties, everything is depending on the crystal direction. So why we mainly got interested into this material is because, as you can see on the periodic table, it's the phosphorus atoms, phosphor atom is the neighbor to the silicon, which is kind of the star material for spin transport. It has light atoms, so spin orbit coupling should be small. And also, it's a centrosymmetric material, meaning that you would also expect Elliott-Yaffe type spin scattering mechanism, which kind of suggests that if you have higher mobilities, then you would have much higher spin transport properties. So today I will not go detailed, but I will not even mention, but it has also 1/2 nuclear spin that we have lots of some experimental indication. So the material is expected to be very rich for spin physics, and that was the main reason we started. But the material has one major obstacle. So if you would exfoliate the material here and then just leave on the table for Indeed, this is like relatively thick crystal. If the material is below 5 nanometer, the material will just degrade completely within half an hour. So as you can see, the material is like pristine, and whenever we expose it outside, the material just really just die. So as a first step, we try to develop like a transfer setup in a glove box environment combined with the MB system. And we use the graphene as a contact, so we could show that basically the material, it works identical if you measure in vacuum or in air, and it works like for at least 90 days without having any issue. And the mobilities that we could observe is already up to 4,000 at low temperature. So after learning how to make this material air stable, so for that you really need to do everything in the glove box environment, and then once you develop a effective encapsulation process, then you can take it out and do all the fabrication, etc., outside of the environment. Okay, so this is how the typical spin valves that we are measuring look like. Basically, it has this non-local geometry. We have the charge injection mechanism here, the area here, and then we have the spin area here, and we are just looking the electrochemical potential at the left side of the device. And in case you are not very familiar with the two-dimensional materials, these are how they look. So this is a black phosphorus crystal that we studied. For example, in this case, it was around 5 nanometer. We have a top boron nitride layer. It's very difficult to see. You need AFM, etc., to be able to identify the thickness. And this boron nitride crystal on top is required for two purposes. So the first purpose is, of course, to encapsulate it from the degradation in the air. So we have seen that if you encapsulate it with the boron nitride, it's very stable. And the second thing is we have a problem, something called conductivity mismatch issue, meaning that if the conductivities of your injector electrode and your non-magnetic channel materials are significantly different, then you cannot really effectively inject a spin current into your material. So for that, what you do is you introduce a tunnel barrier. So therefore, we are using these 3 layers of HPN, which is optimized to be the best, in our case, as a tunnel barrier. And the boron nitride that you see underneath is just like, again, it's sandwiching it so that it's completely air stable. So after you make the device, you can just take it out and complete the electrode preparation. So these are the optical pictures before and after the metallization process. So let me just show you very briefly the charge transport characterization of this device, because we have seen quite different behavior. So we intentionally put the boron nitride in under some of the contacts, and some of the contacts, they don't have any boron nitride. And we have compared the charge transport properties of these two devices. So for example, here, the area where there is no HPN under the cobalt, you have this typical P-type behavior of the black phosphorus. And whenever you study the device with the 3 layer of HPN underneath, the material the transistor become an N-type transistor. And we have done some calculations with our collaborator, Koek-Soo Ying. And what happens is indeed like the effective work function of cobalt is reduced if you insert a thin HPN. It goes from 4.8 EV to around 3.8 EV. So there were also very similar but different direct measurements of this effect by a group in Colombia, which they also demonstrated if you have a thin layer of boron nitride under cobalt, the work function is significantly reduced. So what's happening is whenever you are reducing the effective work function in your device, your Fermi level comes more close to the valence band, therefore you have this p-type behavior. Okay, so this is the first spin transport measurements we have done like 5 years ago. Basically, the sample had around a mobility around 1,500, and we were seeing very clear spin transport in this material, and as well as some the spin precession measurements, and we could extract some important spin transport parameters. For example, the spin lifetimes in this material appear to be around 3 nanoseconds, with the relaxation length exceeding 6 micron. So this is like one of the first demonstration of spin transport in a semiconducting material, and it's the only second material which shows spin transport in two-dimensional limit. So we managed to succeed in inducing the spin into this non-magnetic material, and then they can diffuse over 6 micron. But after 6 micron of length, the spins are dying, right? So we need to understand what's happening so that you can create some new strategies to even further improve. So to understand what we have done is we compare the spin relaxation times with the momentum relaxation times. So these are just spin transport measurements and also 4-terminal charge transport measurements. And then we directly compare their dependency on the temperature. As you can see, both of them are scaling quite similarly with the temperature. And this is very much an indication of Elliott-Yaffe spin scattering mechanism, meaning that the spins are mostly relaxing during the momentum relaxation events. And we experimentally have determined the spin mixing probability, a parameter which you can obtain by comparing the spin and momentum relaxation times, and the values are almost exactly matching with what our theoreticians at Regensburg have determined, meaning that in this material that we are prepping in the glove box environment, we are almost approaching to the intrinsic spintronics properties of the material. Okay, so this was the basic characterization of the spin transport in this material. But as I mentioned, the material it has a highly anisotropic crystal structure, meaning that so some edges are terminated with the armchair, the other is zigzag edge, and also it's very puckered. So the question is, if the spins are pointing out of plane or in plane or along the armchair or zigzag edge, does the spin properties change? So to answer this, so we have fabricated new devices by using Raman spectroscopy. We determined the crystal orientation, and then we just put the electrodes accordingly. And even in these devices, we could see quite high mobilities exceeding 4,000 cm square per volt per second. So as I mentioned, one of the issue with the, not issue, but the challenge that we were seeing with the graphene spin valves is you really cannot do any gate voltage dependency because it's a semi-metal. You cannot really turn on and off the charge current propagation much. But in the case of the black phosphorus, it's a semiconductor. And what we have seen is like you can really turn on, and then again turn off spin propagation by just applying gate voltage. And so the first part is just coming from the fact that the materials are insulating at this gate voltage regime. Indeed, it already becomes conducting much before, but because of this conductive mismatch issue, you cannot really still effectively inject. And then there is a region where you can transport the spin current very successfully. And then later on, even though the device is conducting very well, so you cannot really again propagate any spin current inside. It's just because you cannot effectively inject the spin current inside. And we have done some very simple simulations by following the Ferd and Jeffrey's spin diffusion theory. And what we see is like it's just coming from the fact that conductivity mismatch issue kicks in just because of some computation between the contact resistance, also the spin, the resistance of the spin the channel material. Okay, so, and then we start to study the spin anisotropy. Basically, this is the typical Hanle measurements that I showed several times. And whenever we start to apply much higher fields, then as I mentioned, the injector and detector electrodes, the polarization direction is forced to be out of plane. So basically, now you can compare the spin signal coming while your spins are pointing out of plane versus in plane. So we have done some simple calculations, and what we do see is, like, surprisingly, the spin relaxation times for the spins pointing in the out of plane direction, they are nearly 5 times better than the in plane. So for example, in this device, we were measuring around 1 nanosecond spin lifetimes for spins pointing in the plane, and versus if you force these spins to be out of plane, it was exceeding 6 nanoseconds. And so as you can see here, we are just applying the negative field, but if you also apply the positive field, either the injector and detectors are polarized like this or like this, so in both cases they are parallel with respect to each other, so you get the same amount of the signal. And so this is the spin valve signal that I have shown in many material systems, and it's kind of a rectangular type signal. But what we do see is whenever we are measuring this high mobility black phosphorus spin valves, in addition to this spin valve signal, we do see some kind of spin relaxation near the zero field. And so we call this ordinary spin valve versus the anisotropic case. And similar results were also obtained in spin valves with the germanium. Basically, both germanium and also in the case of the black phosphorus, we have the G-factor anisotropy, meaning that even though you are applying only the fields with respect to the in-plane, so the spins are also feeling in a perpendicular or different direction, effective different direction of the magnetic fields. Therefore, you start to have some kind of relaxation near the zero field. Okay, so by now we know that the spins pointing out of plane, they are living much longer than the in-plane one. But the question is, does it matter if the spins are pointing along the armchair or zigzag direction? Indeed, it should, because the electronic mobilities are different, so the effective masses are different along the armchair and zigzag directions. So therefore, it's really also important if the spins are pointing in plane or out of plane. So I will not go detailed, but we also managed to determine the anisotropy within the plane. So the anisotropy is, it can be favoring along the armchair direction up to 1.8 times. Okay, so this is like one of the last topic that I want to discuss, and it's something that we are still working on it. And we don't have like very good understanding. So, but let me just give you a brief background. So, if you look at the literature, almost all the spin transport experiments have been performed by using the electrons as the spin carrier. It's just mostly, like in most of the systems, the electrons are lighter. That's maybe one of the reasons that the groups are mostly focusing on electrons. So it's also similar in black phosphorus. So indeed, the effective mass for electrons are smaller than holes. But what we do see is, if you, so this is a two-dimensional material. Basically, you can apply gate voltage. You can change the carrier concentration as well as the type of the charge carriers. So for example, at this region, or dominant charge carriers are holes, and in this region is electrons. So we can perform the spin transport experiments by just applying the gate voltage. And this is indeed one of the unique aspects of two-dimensional materials, because if you want to do these experiments with the, let's say, with the silicon, you need to bombard it with the foreign atoms, so you are also inducing some new waves of the momentum scattering. But in this case, you are just applying electric field. You are not changing anything about the crystal structure. And it also allows you to directly compare the spins once they are carried by holes versus the electrons. So what we do see is, so the mobilities for electron and holes appear to be in our device were almost identical, around 800 cm square. But what we do see is like whenever the spins are carried by holes, we do see like almost 10 times better signal compared to electron case. And whenever we are studying the spin relaxation times as a function of the hole concentration, as you can see, these spin lifetimes, they are exceeding 15 nanoseconds, which is, I think, one of the highest ever measured. So we do see, I think for the first time, with the spin transport with the holes under non-local geometry, and very surprisingly, the spin properties are much, much better than electrons itself. And I'm saying that we are trying to still understand because there is this theoretical limit. We are even measuring better than the theoretical limit, so it looks like we need to revisit the theory side as well. Okay, so with this, I'm summarizing my talk. So basically, I hope you got convinced that the black phosphorus is a highly interesting material for spin transport. Indeed, we have seen much more. We are also observing the indication of the hyperfine interactions, etc. So in terms of the spin physics, especially this hyperfine physics and also the peculiar crystal structure is making this material quite interesting for spin-dependent studies. And by developing a very effective encapsulation process, we can make this material air stable, and we can observe spin lifetimes exceeding nanoseconds. And because of this pocket crystal structure, its electronic properties or the Raman properties, the vibrations, everything is anisotropic. We do also see that the spin transport properties are anisotropic in this material. So basically, by combining this material with some other 2D materials that I cannot go into detail, you can control you can control the spin propagation within this material by just making some van der Waals structures by also using other materials with high spin-orbit coupling. And we have full gate control, meaning that we can turn on and off effectively by using the gate voltages. And let me show you here first the spin lifetimes compared to the other star materials. So here I already listed materials like silicon, gallium arsenide, germanium, graphene, etc. So indeed, only our group has been working on black phosphorus, so it's relatively new material for spin transport. But what we do see is like spin transport properties are already comparable, even better than the state-of-art materials. And another important feature of the black phosphorus, I do believe, is the observation of extremely large spin signals. So we do perform with this four-terminal geometry, and compared to, for example, even in graphene, we do observe significantly longer signals. And this is also quite helping in terms of using this spin transport for spin torque studies, etc. Okay, so as I mentioned, I just recently moved to National University of Singapore, and we are very interested to expand this research by combining with the van der Waals magnets, etc., and also studying some superconductors for spin triplets, etc., as our new research. And in our group, we have lots of openings for PhD students and postdocs, and especially if you know anyone would be interested experiencing Asia plus some low temperature physics, I would be glad to discuss. So I just moved, but I'm already working closely with other groups which have state-of-art facilities, and my lab will be fully operational in December. So with that, I would like to also acknowledge the collaborators. So my former student, Luke, he was doing lots of work with the black phosphorus anisotropy studies, and Prof. Barbaros and his postdocs helping with the black phosphorus experiments. And the crystals were grown by the Japanese group, Prof. Takashi Taniguchi and Watanabe. And the theory for the black phosphorus, the first characterization was done with the help of Prof. Yaroslav Fabian. So thank you so much, and if you have any question, I will be glad to answer.
We thank our speaker for the nice presentation. Now we can receive the questions. Anyone to ask? Please.
Yes, thank you for a nice talk. I have a question. So, in case of single electron devices constructed from a chain of coupled semiconductor quantum dots, you can also observe spin transport.
Yes.
So, is there any way to transfer some of your results or your methodology to such system?
Yeah, so during my postdoc, I tried a lot working on the constraint, like single electrons, etc., the devices. And so far there is no study, but in principle it should be possible.
I see.
And so it was quite challenging for us to fabricate these devices, nanoconstrictions and studying in detail.
And second question, in regard to diffusion, spin diffusion theory. So the differential equations are linear equations,
yes,
which you have shown. Is there a possibility of existence some nonlinear term in case of many spin presence?
Yeah, possible. So we are just assuming that our injection mechanism, everything is based on the tunneling, and this is just the theory which is having this component. But yeah, I don't know. So with the electrical measurements, this is what we are getting.
Thank you.
Please, Laura.
Thank you for a beautiful talk, and I think I want to be your postdoc. But I just had a really basic question about the materials. And you were talking about the importance of contact resistance for spin transport and how you'd have to go to a barrier. So what you make a tunnel barrier, yes, to increase the spin transport. And I didn't quite understand that. Could you explain that?
Yeah, so if the resistance of your contact material and the non-magnetic material, if their conductivities are too different, so what's happening is basically, so your contact material is a ferromagnet, a metal, and this is a semiconductor, so their conductivities are significantly different. And whenever you are trying to inject the spins are trying to backflow. And so there was a theory, it was suggested that if you can introduce a tunnel barrier in between, you can combat this issue. Basically by just increasing the contact resistance so that you can stop the backflow of the spins. But there must be a balance that it shouldn't be that transparent, but also it shouldn't be that high resistance, otherwise you cannot really effectively inject any charge in your devices. So we have done this experiment by varying the thickness of the boron nitride crystal. Basically, as you would expect for insulating material like boron nitride, the contact resistance depends exponentially with the thickness. So we have seen that the 3 layers of HBN is the most optimum thickness so that we can still effectively inject the charge with the spin, but the spins do not backflow. But if we repeat the experiment for example, with monolayer HBN, the contact resistance is significantly less. You can easily inject much more current, but you don't see any spin transport.
Very interesting. Thank you very much.
Very difficult as well.
Do we have another question, please?
So you have shown so that the spin transport or spin relaxation time for the in-plane and out-of-plane direction is significantly different. Do you have some understanding of the underlying mechanism of why it is so?
Yeah, so this is a good question. I can't tell, we have very good understanding what's happening because the theory was predicting that the spin lifetimes within the plane should be higher than the out of plane. But experimentally, we are kind of seeing that out-of-plane lifetimes in multiple devices are much better than the in-plane. And we associated that one to this G-factor anisotropy, meaning that there is kind of like a spin orbit, intrinsic spin orbit within the material which are forcing the spins to be lying out of plane.
So it's not related to the anisotropy of the crystal structure?
I think it's just the intrinsic property of the material, nothing to do with the crystal structure.
Yes, there have been some reports of bilayer black phosphorus being, the transport properties being affected by twisting.
Oh, yes.
So the question is here, can you increase the spin anisotropy by structural effects?
Yeah, definitely, it should be possible. But the issue is like even in the case of the graphene, having these twisted samples fabrication, their stability are major problems. And note that the black phosphorus is highly degrading material, so we are very careful with these experiments. So in theory it's possible, but experimentally extremely challenging for us at this moment. So we are trying to do this kind of device by making a new kind of facility, doing this transfer process in high vacuum conditions, but still we have lots of way to go.
We have time to take another question. Please.
So I understand you're still working with flakes. What are the prospects of making this material at a wafer scale, if you can talk about the next generation of technologies?
Okay, so I mean, for graphene, for example, it took, I guess, at least 6-7 years to go to the wafer scale. And for black phosphorus, there are some studies that they can do in the wafer scale, but it's not as good as graphene. So again, note that this is like highly air-sensitive material. So the issue is like these materials, they are much more air-sensitive once they're extremely thin in monolayer limits. So all the experiments that I have shown, they have the thickness around 5 to 10 nanometer. So, but the growth is getting more trickier once you try to grow like multi layers, layer by layer. And if you would manage to grow the wafer scale of the black phosphorus, the phosphorine coal, it could be possible, but it wouldn't be air stable, right? So therefore, I think the main challenge is with this material to be anything applied is learning how to grow wafer scale in a thicker regime. So, but as far as I know, there is no direct study or the experimental realization of the wafer scale growth of this material yet.
But do all these properties remain if you grow thicker layers, or are they associated with a very thin two-dimensional layer?
Sorry, say again?
You said that there's a problem with growing, the solution is to grow thicker layers, but if
Yeah.
you grow thicker layers, do all your properties disappear? Are they a
No,
function
no,
of
so
the
all the things that I have shown, they are working in the thicker region. So in the thinner region, we didn't study because mobilities are significantly less than this thickness range. So we intentionally selected this 5 nanometer range where you observe the highest electronic mobilities. So that's why we focus. But if the Elliott-Yaffe type mechanism is valid for ultra-thin limit, then your spin transfer properties would be less compared to these results. So that's why I do believe that if one really considers this material, it has to go around 5 nanometer range. And for that, you need to grow layer by layer, around 10 layers.
Okay. Let us thank again our speaker for the nice presentation. I would like to
So now we can go to the last lecture of this session, which will be delivered by Professor Laura Green, and it's entitled The Dark Energy of Quantum Materials, a Multidimensional Playground in Superconductivity.
Thank you very much. Well, thank you very much. And this is a hard act to follow. I don't have the clicker. Okay, now I have the clicker. I learned to buy clothes with pockets now. So it's a real pleasure to be here. I want to thank the organizers. Ali, you're doing a great job. All the organizers have, and it's a beautiful place. And so I'm a little worried I'm keeping you away from your welcome cocktail, but Ali said he's moving things back a little bit, so you'll still get your cocktail. So anyhow, the title of my talk, it's a little longer, but I'll just say it shortly. I came up with a fun analogy a few years ago, and I'm going to talk about that. So I'm doing a lot of different things right now. All right, there we go. So why do I have this title? I have this title just because I've been doing quantum materials for many, many years, and this is an overview that I looked at that helps us understand how complex this problem really is. So it's a really public engagement, and it's become sort of my view from what I fly a lot, so like at 35,000 feet up, what it looks like. And so one thing I like to point out is that in quantum materials, there are many, many unsolved questions, and that's what I'm going to bring up most here, if I get to it at the end. And these questions are certainly no less fundamental, and that's a point that I really want to bring home, than anything you have in cosmology or high energy physics. And I like to point out that there are many things that we have in common, and I'll do a fun analogy. Don't take the analogy too seriously because I really don't know enough about it. But colliding black holes create gravity waves on the order of 10 to the 26 meters wide and 10 to the 49 watts. And a lot of these quantum materials are things that form clumps, like electronic nematicity, stripes, et cetera. And these are on the order of 10 to the minus 10 meters or 10 to the minus 21 watts. And so the difference is in 10 to the 36 in length and 10 to the 70th in power. I'm not saying they're identical, but a lot of the mathematics and a lot of the ideas really do correlate. So the outline is I'm going to spend a lot of the time talking about the National High Magnetic Field Laboratory. I'm finding since I've been there, that's what people really want to hear about, how broad it is, how interesting it is. And then I'm going to tell you what the definition is between a conventional and an unconventional superconductor. And it really helps, especially young people, put these in a different perspective. If I have time for my analogy, I'll do that. I probably won't have time. This is something that I won't be talking about here, but if I have time, I'll flash a slide. And there's a lot of great progress that's happened in quantum materials, and still a lot of questions to go. And I like to warn you that I love to use analogies, pretending if you're swimming in a lattice or something like that. But if you push any analogy too far, it breaks down. And I like to bring that up because in quantum mechanics, we have to use analogies. And the most favorite one is the Bohr model of the atom. We love it, we teach it, we use it, and it's completely wrong. So there are useful analogies. Now, onto the National High Magnetic Field Laboratory. No one could remember NHMFL or NHMBFQ, anyhow. So we just call it the Magnet Lab or the Mag Lab. So our mission is to operate a world-leading high magnetic field user program. We are primarily a user program. Carry out in-house research in support of the user program. And we do have some terrific in-house research that's going on. Maintain the facility and develop new instrumentation. And I'll show you some things that we're really moving along there. And another thing, because we're supported, our core grant is from the National Science Foundation, not from the Department of Energy, not from Commerce, et cetera, we are charged with having a strong educational and outreach program. So moving along, I keep doing it on this one. So this is just to give you an idea of the National Magnet Lab. So we have 3 campuses. The main campus is in Tallahassee, which is northern Florida. I'll show you a map in a minute. It's basically southern Georgia, and it's a very, what did I do wrong here? So if you hold, okay. It's a very, very large facility. If I go from my office to my lab, my Apple Watch rings close in half a day. It's really, if you have a chance to see it, you really can't really appreciate how vast it is. Now in Tallahassee, there's a map here with Florida State up there, there's the United States. We have the strongest magnet in the world within error bars, which is a 45 Tesla hybrid magnet. By hybrid, we mean it's a combination of a resistive magnet and a superconducting magnet. And we can also do 21 Tesla NMR research. In Gainesville, at the University of Florida, I'll be showing some examples here, we have 2 user facilities. One of the user facilities is the high B over T facility, which doesn't go as high field, but it goes to very low temperatures. So you have the highest B over T in the world. And then people love these things, so I'm going to show you several examples where we do advanced magnetic resonance imaging. It's called AMRIS, the Advanced Magnetic Resonance Imaging and Spectroscopy Facility. And we do MRI up to 21 Tesla, and we can do in vivo MRI. And I just came from Los Alamos, which is why it took me almost 53 hours to get here. And at Los Alamos, we have a 101 pulse magnet, which is the most reliable pulse magnet in the world. However, here's a great picture. So this is the rotor that produces the high magnetic fields, and that's a normal sized person. So if you can, it's really big. And if you're interested, I've got a long history of it. I can share it with you if I have time. But anyhow, it's about 101 Tesla pulse. So here's our Delta Airlines map of the Magna Lab. So what we have here is that in 2019, the Mag Lab hosted over 2,000 users in over 152 institutions. That number has gone up. We had a little hit because of COVID, but the numbers are back up higher than ever. And here are the facilities that you can see the people. This is the 2019 Delta Airlines map. That's Gainesville in the light blue, and purple is Tallahassee, and the red lines are Los Alamos. Okay, so we see people from all over the world. About 300 institutions, that's probably increasing. And one thing that I'd like to point out, if you look at some of those lines there, you'll see that they originate in Wuhan, in Hefei, in Toulouse, in Dresden, places where there already exist magnet labs. And we do work in each other's labs, and it's a great collaboration. But they want to use our probes, and they want to use our magnets. I want to point out also, I'm going to advertise this, newcomers are welcome. Yes, we're oversubscribed, but we're looking for new people all the time because we want to have turnaround and diversity. And typically every year, about 25 to 30% of our PIs have never used the Magnet Lab before. So our Mag Lab faculty are very good at working with first-time users. And you have to write a short proposal, and you're welcome to contact a Mag Lab faculty, I'll show you a slide later, and ask them to help you write the proposal. We just want to help you get the science done. And so we'd like you to come and visit. And I always say it's free to use. If your work is publishable, it's free to use the facility. You just have to get there. And if you won't be there for too long, you can stay with me. I have a big house. The other argument that we have, why would the NSF put that money into a facility? Well, the bang for the buck, the respected papers per dollar is really very high. And we also do things that you just can't do in a single PI in their home institution. And I'll show you some of the reasons there. Now we have here just showing that we have different kinds of magnets. And so this is our short pulsed. Our short pulsed is being rewound now. They found a problem with it. It's a great story. But while it's being rewound, we went back to what the other labs use and use capacitor banks. They're less reliable, but we now have a 75 Tesla pulse field that we just built while this thing was down. But you can see we have all these magnets. So we will be building the 60 Tesla magnet. We have the 45.5T. That's a DC magnet, by the way. I mean, that's not a superconducting magnet. One thing that we won the R&D Top 100 of the Year award that was just announced was we have a 36 Tesla all superconducting magnet user facility. This is way above what anyone can do, so we're really proud of that. It's very useful. Some of our big hits, not only besides the 30 Tesla, we have something called a 36 Tesla series connected hybrid. Without going into details, it's very homogeneous, very stable, and you can do imaging at 36 Tesla. And some of the other things, this here was in 2018, they made a 45.5 high temperature superconducting test coil. And among other things, and the success in our 30 Tesla all superconducting magnet, the National Science Foundation just funded us the design funds for a 40 Tesla superconducting magnet. So we're very excited about that. Now this is the fun part where I'm going to talk about some science, and there are going to be overviews, and I don't know if I can answer all the detailed questions, but as chief scientist, this is part of my job. Our main areas of research are materials, energy, and life. So I'll just show you some materials examples. So this is one that really had people, it just started a whole new field of research. It's this heavy fermion, uranium tellurium, I do this all the time, don't I? Uranium tellurium-2. And what was found was that if you apply, as many of you know, I'm not going to be giving a public lecture, I'm going to assume you know what a superconductor is, that if you apply a field to a superconductor, you break the superconductivity. So we have here, as a function of angle in the uranium tellurium-2, if you apply a certain field, this white area is where it's not superconducting anymore. Okay? If you then increase, and what's interesting at this angle, the superconductivity lasts up to 35 Tesla. Now let's change angles here. As you go into a certain angle, up above 35 Tesla, all the way up to 60 Tesla, so this was done both in our DC and our pulsed field user facility, they found that a new kind of superconductivity evolved. They called it a Lazarus because it's woken up, you know. But basically, this is completely new, and it's not understood. It was a complete surprise. It looks like a triplet superconductor. There's a lot of studies going on, and it's been a very interesting and fruitful area of research. This one I'm glad I threw in here because this Ahmet might be interested in. So this is all still prototype. This is some of the spin transport they were doing on our electron magnetic resonance area. So this is EMR. They also call it electron paramagnetic resonance, depending on where you've been. But what we have here is an antiferromagnet that's attached to a non-magnet, okay? So this is a heavy metal, platinum, magnesium difluoride, and you send in terahertz radiation, and you get a spin transport across, and you can bring out ultra-fast electrical signals. So it's spin transport through this platinum. Now, what happens is it's 2 to 3 times orders of magnitude. It's 2 to 3 orders of magnitude faster than your standard ferromagnetic devices that people study. And the reason for that is this coupling is due to exchange. It's not due to magnetic anisotropy. So that's been a fun thing to study. So it's promising for spintromics devices and who knows what else. So this is just an aside more on materials. I'd like to point out that superconductivity and high energy physics, if you don't know, they've been buddies for decades and decades. And here we were making, I wasn't, but they were making superconducting devices for bubble chambers. And now we're playing a major role in the high luminosity upgrade of CERN. So, I'm going to say also this, that the largest funder of superconducting materials on the planet is the Department of Energy's High Energy Physics program. And they help keep our Applied Superconductivity Center going. And so our Applied Superconductivity Center and our Magnet Science and Technology Centers, these are 2 labs that aren't user facilities, work very closely with the high energy community. And we've invented some new materials. So most of you probably know that if you go into an MRI, the standard, if you're using a magnet, is niobium titanium because it's malleable. The 815s, like niobium 310, have a higher TC, a higher HC2. I mean, not a higher TC. Yeah, they do. A higher TC, higher HC2, and higher JC. But they're harder to use. They're compounds. So if you have to like wind them and then fire them. But we've done some work in increasing the JC so much of niobium 310 that it's being used in the high luminosity upgrade, which is expected to increase the luminosity in CERN by a factor of 10. And those magnets are being shipped. It's a combination with the Magnet Lab, Fermi Lab, Argonne, and also LBNL.
So we're, oh yeah, and then we actually have a new one. There's a new niobium-3 tin with hafnium doping that we're looking at because that is very promising for the linear collider, LHC. And I want to point out that I've seen Fabiola, I've met her several times, I've seen her give talks, the Director General of CERN, and the mag lab is all over her slides, and she says the only thing that's limiting our luminosity are the magnets. So it's nice to be useful to other fields. Now I'm going on to examples for energy. These I think you're going to like. Most of this you wouldn't have known about. And I love to focus on our ion cyclotron resonance facility. It's also called Fourier transform ion cyclotron resonance, ICR. I did not even know about this until I started coming to the mag lab a lot more. So what this is a mass spectrometer that is on steroids. It uses a 21 Tesla magnet, and you can get, you throw and you spit in a little complex fluid, start the cyclotron resonance, chirp it, and you get a band like this, a comb like this, and this comb, you can separate out in complex fluids and get mass resolution of about an electron. So why do you want to do this? Well, this was developed first for petroleomics. So, for instance, the most complex fluid on the planet is petroleum. So if Exxon and BP are drilling in the Gulf of Mexico and they both hit oil reserves, they want to know if they hit the same reserve or not because it costs $1 billion to dig a hole to go looking for oil. And so this technique, and we do work for them, and they pay for it. They don't get to use it for free. But we can fingerprint the oil well enough to know exactly where it came from. It's also used for forensics. If an oil spill happens, even if it's much, much later, we can look at the makeup of the oil and tell you exactly which oil head it came out of. And so then we've applied this to a couple other things. What I won't spend a lot of time with, I'll have more examples of sustainability, but proteinomics. So this is so accurate that you can actually tell the difference between folding and proteins. The most popular protein is the p53. As many of you might know, that the folding of a protein determines its functionality. And by doing a hydrogen-deuterium exchange, you can tell what the folding is and tell if p53 is, and it's well known that this can be a completely healthy, neoplastic, or malignant protein. So that's very interesting. And then finally, for climate change and sustainability, it turns out we also look at like the second most complex fluid, which is dissolved organic carbon and PFAS. So I'm going to say a minute about those. So here's one thing that we do here, looking at climate change. So you go up into the Arctic and you take samples, and you can tell how the carbon in the ice and in that area changes as a function of latitude and also time. And you can tell, for instance, this is what no one else can do in this, is you can tell if the carbon, dissolved organic carbon, is in the shape of an island structure or in the shape of an archipelago structure. And one's good and one's bad. To be honest, this is the one that's better because you can separate. The water soluble, which is the one that's so difficult to get, it's so complex, is you want to be able to get, this is the good one because you want to be able to get the tar out of the carbon. So this is an example, and you're looking at these things that are about 1 electron mass separated. Okay, so here's another one that just came out a few months ago. So when you leave, there's something called PFAS, which are long-chain fluorine-containing molecules, and they're very bad for you. They're carcinogenic and they're terrible, and they're in plastic bags, they're in a whole bunch of things, they're in asphalt. And that's something that Amy McKenna at the Magnet Lab studies in great detail. And she found something recently, which was that if you leave a plastic bag out in the sun, it was thought that PFAS never decompose. The PFAS does decompose. They're studying those decomposed elements now, and we don't know if those decomposed elements are more dangerous than the PFAS are, which are already pretty dangerous. And there's a lot of, I can go on forever on this, but rather than doing that, rather than going on to this, and I'd love to talk about it, I want to talk about some of the life examples. These are all from, everything I showed you up to there was either from, mostly from Tallahassee, a little bit from Los Alamos. These next ones are from University of Florida in our Amherst facility, which is in the McKnight Brain Building. It's a fantastic facility. So here's one example. So how many people have been in an MRI? Probably anyone over about 25 has, yeah. So the best thing about an MRI is you get to go inside of a superconducting magnet, right? That's very cool. But the MRIs that you get in the hospital are 3 and 5 Tesla. There's a lot of reasons for that. One of the reasons is that you can do it, okay? Another reason is that if you don't really want to go too much higher, because if you increase the magnetic field, you have to increase the RF field in which you're measuring, right? You have a resonance conditions between the field and the RF field in which you do the magnetic resonance imaging with. So typically what you have is that you can see about a 1 millimeter resolution. But if you go up to what we can go up to, which is 21 Tesla, you can go to micron, a 10 micron resolution. So you can see things much better. And so you don't want to look at too many living things. You can for a short time. But here's an example of imaging by MRI of a frog brain. So now we can see subcellular structures. So one example is that still using 21 Tesla at the Magnet Lab, we have shown that you can actually, so if you're looking, Alzheimer's disease is believed now to be generated from plaque amyloids that build up in the brain. And it turns out that we could now have the earliest detection of this. We can't do it with human brains yet. These are still rat brains and small animal brains. The biggest diameter is about this much for this in vivo stuff. But what happens is that when the plaques form, they create microhemorrhages. And boy, when you do MRI, that's what you can see, right? When you do MRI, you pick up the hydrogen. So here you're looking at, I don't know if you know this, but when you do MRI, you're looking at protons in the hydrogen, and that's where you're imaging. And so if you increase the field, you have to increase the RF. It's a much higher frequency, so that is a shorter wavelength, and it gives you higher resolution. So the plan is, and in Florida we do a lot of work for aging, the plan is that if you start getting that's the plan. If you start getting other symptoms of Alzheimer's, like loss of taste, et cetera, it might be COVID, but there are other symptoms. Maybe we could look for early plaque amyloid in the brain. So another one that's very interesting. Oh, you know what? I should do this one first. Yeah, I should do this one. No, I'll go to this one. No, I'll go to this one. I just changed my mind again. So here's something that I put in here because it has to do with gadolinium nanoparticles. So it turns out that one of the things that people are looking at for stroke, for healing stroke damage or any brain damage, is injecting stem cells. This is a very new result, was that what they were able to do, and in vivo means we're looking at a living mouse, okay? A living mouse they had a stroke, and you can inject stem cells, but you could label them with gadolinium, attach them to the stem cells, and then you can see how they move around the brain and understand where the damage is. So that's extremely new at the Magnet Lab, and the one that I went over, which everybody loves, is this one here, which is for cancer detection. And again, this is still a prototype. We do something called, so I mentioned that when you do MRI, you're looking at water, you're looking at the hydrogen in water. They call it proton MRI. Okay? But what if we decided to look at something besides hydrogen? What if we call that unlocking the periodic table. So in all of our resonance facilities, MRI, NMR, and ICR, we can look at all kinds of different isotopes. So here's one example, and that is looking at sodium. Now, if you look at sodium, it's a lot heavier than hydrogen, so you can use a lower frequency to do the resonance, so you're going to have lower resolution, but you're specifically focusing on the sodium. So here's an example. It turns out, something I learned when I got to the Magnet Lab, you can buy a rat with a brain tumor. Okay, so here is the image of a brain tumor. It's the sodium in the image that you're looking at. This isn't the proton, this isn't MRI. We're specifically looking at the sodium. Now, it turns out that when cells are dying, they uptake sodium. We don't completely understand why, but they do. So what you do is you image the sodium, you image the tumor, and then you give it chemotherapy, wait 4 days, image it again. Nothing happens, you do that again. And at some point, if the chemotherapy causes the sodium to light up, that means it's uptaking sodium, the cells are probably dying, and that might be a good direction to go, good regime for the chemotherapy. Now this is prototype, but boy, this could certainly be promising in the future, and I'm sure we've all been touched with people that have had to go through this, and to make it shorter and to see the efficacy of the chemo would be very, very important. No, that is the right way. Okay. So this is, just go online, go see what you have. There's all kind. We're redoing the website now, so it's even easier. Pick out what magnets you want. Look around. Also with our education stuff, and we'll help you write it. And it's just fun to look around. And there's all this educational stuff. Magnet Academy, stories, et cetera, et cetera. And I think February 25th we're having our open house where we have 10,000 people show up. Come on over. Okay, it's really fun. So. Anyhow, now I'm going on to the superconductivity part. So I hope it doesn't last too long, but so I just wanted to point out that you did see the bubble chamber before, and in every high energy physics talk you've ever been to, they always show you a picture of the ring. So this is the superconductivity, so I have to show you this figure of Cameron Lachonis discovering superconductivity. I'm required. It's in the job description. So this was a great story because it was serendipitous. So much stuff in superconductivity discovery, new materials, new superconductors, new ways to grow them. It's really so much serendipitousness. And we're all working very hard to do predictive design, but that's the story. So before Cameron Lachonis measured this, what happened was he and Giles Host, who doesn't get credit, he was the technician at the time, but he went on to start Philips Laboratories, so I guess he did okay. No one knew what would happen so they managed to liquefy helium, and out of curiosity, they decided to cool down a wire they made of mercury. And lo and behold, this is what happened, is that, as you all know, that the resistance dropped to 0 at a little over 4 degrees. Their measurement scheme wasn't so good. No one had predicted that. They thought that maybe if you lower the temperature, the resistance would go up, it would go linearly to 0, and people had their theories, but this was not expected. That was 1911. It wasn't until 1957 that the microscopic theory of superconductivity was solved. Okay? And it looks so simple now, but it was impossible. And it was a worldwide effort, and Bardeen, Cooper, and Schrieffer managed to, publish the paper, and it's very exciting. And you know what? It worked. It's one of the 2, maybe 3 solved problems in correlated electron physics. So that problem is solved. That's conventional superconductor. And as I think probably all of you know, the answer is not just the BCS theory, but the BCS electron phonon. It's the electrons moving through the lattice, and good superconductors have strong electron phonon interactions, and that's the basic idea, and we kind of understand that. But then these 2 geniuses, Frank Stiglitz, discovered something called heavy fermions, and heavy fermions, I mentioned them earlier, are materials that due to electron-electron interactions, not electron-lattice interactions, electron-electron interactions, the mass of the electron measured thermodynamically is huge. The one that I was growing thin films with was cerium copper-6. It had an M star of 1,000. The one I'm studying a lot now is 85 or 120, but you can't get that from the band structure. And then what happened was Gil Andras started, he was really big on this pressure stuff. I just talked to these guys recently. Big on this pressure stuff, and he discovered this phase diagram. Okay? So this phase diagram is super important. We talk about it all the time. If you've worked in high TC, you're very, very sick of hearing about it. And, but this is it. And that what we have here on the y-axis is temperature. On the x-axis is a thermodynamic variable. In this case, it's pressure. And I don't do pressure measurements. I have done, but mostly I do doping, and I'll show you some examples. But what we have here that's really so interesting is that what's so surprising is that we have antiferromagnetism on one side and Fermi liquid, a normal metal, on the other side. And here's the crossover across this line here. And then when you get down to lower temperature, these phases fight each other, which is determined to be a quantum critical point in most of these things, and this dome of superconductivity appears. Why does that happen? Very interesting. But the fact that it's near magnetism, as we all know, conventional superconductors really hate magnetism, right? And so, why does magnetism all of a sudden good for superconductivity? And it became clear that BCS electron-phonon coupling couldn't be the only story here. So moving right along, you've seen this. If you've been in superconductivity, you've seen this a million times. I just like to remind everyone about this. Everything in red is solved. Okay, everything in red is solved. These are electron-phonon BCS-coupled superconductors, and it's believed here that the high-pressure hydrogen sulfides and superdeuterides are all electron-phonon BCS. Everything not in red is not BCS. I've only put a very small fraction. I mean, because I'm lazy. I took this from a study I was on a million years ago. But you know, we have here the high-temperature cuprates. We have the iron-based superconductors. We have the heavy fermions, you know, the carbon, all kinds of things. I didn't list the organics. There's a whole bunch I didn't list here. I'll mention them later on. It's like each one of these families is a different universe. They really, you know, I have papers that show, and I've been on papers that show that not only do these different families have different mechanisms for causing the electrons to pair into Cooper pairs and become superconducting. But even, I have one paper with Dirk Vandermeer that going across the doping area changes it. Now, let me just also tell you about this dome here. Almost every one of these families of superconductors has a similar phase diagram to this. Okay? This is quantum mechanics. You will find an exception. Okay? But pretty much all the families have something that look like this. And I think I blew it up on the next one. Yeah, so here I've blown this up. And so we have the y-axis is temperature. The x-axis is a thermodynamic variable, typically pressure or doping. You can use magnetic field in some cases. But in any case, on the low pressure, you know, ambient pressure, low doping side of the phase diagram, you typically have an antiferromagnetic insulator, typically. Over on the right-hand side, you typically have a Fermi liquid. And when they cross over, what you have, which in almost every case, above the superconducting dome that I mentioned earlier, you have what I call unsolved quantum matter. So again, the devil is in the details, right? We don't, you know, whether it's dematicity, stripes, whatever, we don't really understand all this, or the pseudo gap. But what I will say is that that's where the interesting part is. And I think my next, or somewhere I have another figure on that, which is, okay, if I get time for my analogy, I'll say this later. For those of you that have ever done any, or actually taken solid state physics, or whatever they call it now, you know that we know how to solve Fermi liquids, right? It's what's in there. Is it gold? Is it silicon? Is it copper? And we just figure out what it is and the crystal structure, and we get the thermodynamic properties, right? We get the optical, transport, and you know, whatever thermodynamic properties from these, you know, DFT, whatever measurements you're using. Okay, that's pretty easy. But if you, and I also want to point out that if you go under the dome, and I've looked at enough of a variety of superconductors to know that you can get those properties too. Okay? We don't know what causes, exactly what causes the pairing, but they're still Cooper pairs. All the superconductors to date are still Cooper pairs. So we can use the Bogoliubov-Degen equations and solve what the electronic transport and thermodynamic properties are. And if it's D-wave, you put in a D-wave kernel. If it's multiband, it's a little more difficult, but you can calculate those properties. What you can't do, what we don't know how to do, and there's some progress, is calculating the properties above the dome there. So that's pretty much what I study when I do this work. And so this is just to, you know, confuse you, which was that I just threw up a bunch of superconductors up there and showed they all have this dome. So here's the one I showed you earlier, okay? And I'm I'm having trouble with the pointer. Here's the upper left is what I showed you earlier. There's the cuprates, there's organics, there's the dichalcogenized, twisted bilayer graphene. They all show these domes. And what I didn't throw in here, maybe I should have, is that there's this old, nuclear physics plot of the, that shows color superconductivity. And so I don't know if you've seen that one, but it's always fun. But this is ubiquitous. This is ubiquitous. But the devil is in the details. What is going on above the dome in every one of these is very, very different, even though they all have this interesting shape. And I also like to point out, and this was, I forget who said this first, it wasn't me, but this dome is so interesting because if you go, it's a dome, which means it's big in the middle and lower on the sides, which means if you're too weakly coupled on the right, a Fermi liquid is a weakly coupled, metal. On the left side, you're strongly coupled. If you're an if you're a Mott insulator or a charge transfer insulator, that's as strongly coupled as you can get. So the cuprates, which are charge transfer or Mott insulators, depending who you talk to, they're, it's very strongly coupled. So TC goes down on the right when it's too weakly coupled. It goes down on the left when it's too strongly coupled. These areas are robbing spectral weight from the superconducting area. So, but you need this stuff. You need those strong correlations and this funny stuff to get this high temperature superconductivity. And that's not really understood. What's going on in that delicate balance of the non-correlated and extremely highly correlated electrons. So that's why I think it's so interesting. And then just to show you again, I think you all know some of this. These are just pictures of some of what you can see that I call the unsolved quantum matter. And this is, I'm just showing this again. There's the nematicity on the upper right. There's, I had to throw some of my data in there, so that's mine at the lower left, measuring the nematicity, stripes, charge density waves in the cuprate, charge density waves in the dichalcogenides. You're not going to learn these right now, but I'm just trying to tell you that there are many, many, many kinds of electron correlations that give you this, quote, unsolved quantum matter. So, and besides there being many, many universes of unsolved quantum matter, there are many, many, many microscopes to how to measure these things, right? We have all kinds of ways to measure these things. Some of them are new, like RICS, quantum oscillations to measure the Fermi surfaces. We do a lot at the Magnet Lab. That's a picture on the right there. Some of the work that I do, just understand, and you'll hear about these here, there is a wide suite of measurements, some new and some just greatly improved. There's also a wide, wide suite of calculations that are being created that are astounding. And there's also the quality of the crystals being grown is another thing that's astounding. Some of the experiments that I published on very recently were not even possible 4 years ago. That's how well people are growing the material. So that's pretty exciting. So that's helping us create these. So now I can almost get to my, do I have a couple more minutes? 7. Okay, I could do this in 7. Okay, so there's unsolved quantum matter. What I mentioned before, Fermi liquids, solved. Fermi liquids, simple metal, we know how to do that. It's the crystal structure and the atoms in the crystal. And we understand how to do superconductors. So let's just put those aside. What we don't know how is to calculate this interesting electron matter or unsolved. So how do we know it's there? So basically, if it's not a Fermi liquid, then the electronic properties cannot be determined by the crystal structure and what's in it, right? Because the electron-electron correlations are so strong. And the second one, which I think of as an experimentalist, is that the electrons break the symmetry of the underlying lattice, right? In the nematic phase, the electrons will pop in like sausages or cigars, depending on what you like, and they're on top of a tetragonal lattice. So the symmetry breaking, and it's just not a solved problem. So moving along here, conventional superconductors, they're typically less than 40K, like niobium, niobium-310, and at high temperature, it's solved. It's a Fermi liquid. At low temperature, they're superconducting pairs. So you go from high temperature, where you have a simple Fermi liquid into a phase transition, it's a real phase transition, right? You're creating and destroying quasi-particles and Cooper pairs. It's really cool. But it's solved. We got this one. What we don't have is this one. So just saying it rather quickly, on the far right side of the phase diagram is a Fermi liquid. And then below TC are Cooper pairs. They may not be electron-phonon coupled, but they're Cooper pairs. So those are solved. Most of the rest of the phase diagram are these interesting problems, which there's success, but there's still a lot of them. We're still working on them. Now, my analogy. So this is just for fun, okay? This is public outreach, and I like to do this. Here we go. So the inspiration was gravity. Actually, before these gentlemen got the Nobel Prize, which was absolutely predicted once they measured the gravity waves, once they did this, I was at a talk that Kip Thorne was giving in Oslo because he just won the Kavli Prize. I was actually on the committee. And he put this picture up there, and he's such a good communicator that I finally got it, right? It's such a great picture, right? What we have is the microscopic theory of gravity is a distortion in the space-time continuum. So then I thought, distortion in the background. And I walked out of that talk, it was a few years ago, and I said, can I make an analogy with BCS? And all my friends thought I'd gone completely crazy. Well, again, I was flying from Oslo to, I think, Denver, which was an applied superconductivity conference, giving a talk there, and I finally worked out the analogy. See, airplanes are really good for something. So this is it. This will give you an idea well, I'll just say this, that it's not a single problem. So let's take a look at LIGO. It was amazing. LIGO measured these gravity waves. Their very first measurement, which I think was, I can't remember, was it 2019? They measured two, did I do that? They're getting mad, I'm running out of time. No, they measured, they measured two black holes colliding. Two black holes colliding. The energy of those gravity waves was more than the combined power of all the stars in the universe for light energy. That's a lot, but it's not light, it's gravity waves. And how did they do it? It was this LIGO detector. And this LIGO detector was this kilometer-long interferometers, okay, kilometers-long interferometers that measured the distortion of less than the width of a proton. So let me just tell you, it was like the best $1 billion the National Science Foundation ever spent. It's an amazing experiment. That's their microscope to get gravity waves. It was predicted, we expected they'd see it, and they saw it, okay? Ours is a little different. Our LIGO is not one problem. There are probably 50 kinds of quantum materials that's above those domes and other quantum materials I didn't even touch that we don't know how to solve. So we don't have one question. We're not looking for a gravity wave. We're looking for a multiverse of questions here, where our microscopes are a combination of our materials qualities, our measurement capabilities, and our theoretical prediction analysis. Excuse me. So here's our analogy. Mr. Newton said, okay, we got this one. M1, M2 over R squared. That works. And it is, and it does on the macroscopic level. Mr. Einstein said, wait a minute, there's a few of these problems like the retrogradation of the perihelion of Mercury, and this isn't quite right. And he came up with a general theory of relativity. And I think he came up with it because, well, he was Einstein. You know, it was really different. And his microscopic theory wasn't just 1 over R squared. It was a distortion in the space-time continuum. To me, one of the greatest successes of LIGO isn't that they measured gravity waves, although that's an astounding success. It's also now, for the first time ever, we have a way to look at the universe that's not light or matter. It's gravity waves. So the big push with people studying this, which I would like to see, is can we understand, using this new telescope, can we get a handle on dark energy or dark matter? I don't know, but that's an outstanding question. And for us, we have Fermi liquid solved, And we have one of the problems solved, which is the BCS electron-phonon theory of superconductivity. Can this plethora of microscopes that we have help us solve our plethora of quantum materials problems? And I've got one more slide before saying goodbye. Okay, 1 minute. So this is just fun, right? Gravity, Newtonian classical. Forces between objects are derived from the mass and their positions, 1 over r squared, and how big the mass is, m1, m2 over r squared. In simple metals and Fermi liquids, the properties are derived from crystal atoms and their positions. So it's kind of an analogy. In the Einstein general theory of relativities, masses create distortion in the background, the space-time continuum. In BCS electron-phonon superconductivity, electrons create distortions in the background. So it's a distortion. But that's just one quantum matter question, okay? So will LIGO help us understand these fundamental questions in cosmology? And will all of our questions, all of our microscopes, help us understand many, many of our quantum materials questions? I'm actually of the belief that you pick one quantum material and stay with it, but that's a belief. And so that's my data. And finally, there's a lot of great questions, and I'm happy to entertain any questions from you. Thank you very much.
Thank you for such a magnificent talk. I think the lecture is open for discussion.
Just don't ask something too technical about gravity.
Yeah, so thank you for a very nice talk and inspirative talk. So the question is, there is some Susskind analogy between wrapped time-space and quantum entanglement. And are you able to map this analogy to superconductivity problem somehow?
I don't think I understand the question.
What
analogy?
Okay,
you asked me a question last time.
there is a Susskind work about wrapped time-space, right? And then there is a certain analogy of 2 black holes in wrapped time-space with quantum entanglement, right?
Oh, yeah, okay.
But since you are dealing with analogy to general relativity that is also expressed by wrapped time-space, you can think about finding such analogy of wrapped time-space to your quantum materials. Do you have any particular example of that or idea of that?
I don't have any off the top of my head. So how confinement or something? I don't know. You know, when the electrons clump together, you have pneumatic phases, there's stripe phases. You know, you do have where they clump together, but I don't know if we'd have to think about it. So I really don't know.
All right, thank you.
Okay. Uh-oh, not Valerie.
Laura, thanks a lot for your absolutely beautiful talk.
This is from Valerie.
Yeah, no. But, okay, no.
Tough guy.
No, but. Okay, come back to slides back.
Oh, wait, I'm going to go the wrong direction.
Oh, wow.
You want this one?
No.
I just want to show my data. Okay.
Where is, okay, here. Okay. Well, I invite everybody
so
to...
what I would like to do is not, don't ask me questions, because I think you'd rather expound on this.
Oh. Well, I wanted...
Go ahead.
Okay, I wanted to invite everybody to the lecture by Carla Trugenberger, because this problem to the right completely solved, and this phase diagram is explained in every detail, and all the properties of, for example, pseudogap state I explained also in every possible detail. And it's understood absolutely completely. And one thing, okay, you didn't have time to, you have to confirm that we didn't agree in advance, that you did your beautiful lecture without...
So who solved all these problems? Because I don't...
It's our paper, okay, Cristina Diamantini,
okay.
She's here, it's published. Carla will be giving a lecture on that.
Okay, I know the one.
And so please come. And there is one property which you didn't have time to mention, and some puzzle. When you have high TC superconductors, there is a beautiful property. You make a thin film, one single, cell of them. And TC of BISCO, for example, is exactly the same as for bulk material. And it's absolutely understandable, because if you take just the usual, well, maybe it's 1 degree difference, yes, that's true, and 69 instead of 70. If you take the usual superconducting materials, make a thin film, then the TC can be just 10 times less, and this is quite normal. In BISCO...
Or it can go up.
Huh?
Or it can go up.
Yeah, well, it's okay. And in all the cuprates, it's not like that. And this small thing is explained as well. So, in this phase diagram is completely explained. So, thank you.
Okay.
It's like great advertisement. Thank you very much.
Thanks. I think we have. Thank you. Yes?
Excuse me.
It's okay. The discussion is very interesting, and that's what's good about meetings, discussion, you know?
Excuse me, I have to comment on the comment, okay? So the fact that TC is not reduced in a single atomic layer for superconductivity is completely understood because the Hohenberg-Mermin-Wagner theorem is ineffective for 2D superconductivity. The reason it is ineffective is that there are not enough infrared fluctuations to destroy TC unless the sample is bigger than the universe. Okay, so there is no reduction of TC from the Hohenberg-Mermin-Wagner theorem in 2D for superconductivity, because the samples are not big enough for this effect. The theorem is mathematically exact, but the samples are not big enough for this to happen. No, I can give you a reference, okay?
I understand what you're saying. What I'm saying is completely different. You take the usual superconducting material, like lead or titanium nitride, or whatever. You make them thin film. Their TC drops 10 times, right?
No.
What?
I don't want to go into a lot of technical details, but no.
No.
You know,
it's a lot
tantalum goes up, aluminum goes up. You can lower niobium by a factor of 2 at the most from disorder.
Okay. If you make it thin enough, the temperature drops, TC. If you take BISCO, the temperature does not. This is the only thing I'm talking about.
Okay.
And okay, that's it. Of course, but it's just one feature.
Yes, please speak on the microphone so everybody online can hear you, like Valerie. Another question or comment? This is a very interesting discussion. This is it's what is nice about meetings. So I encourage you to disagree or agree. I had a question, but it's nothing compared to the discussion. You know, not so interesting compared to the discussion. But maybe some food for thought. When you put this ubiquitous phase diagram, I ask because nobody is asking so far. So when you put this ubiquitous phase diagram, if you put them there, there's a difference between those types of compounds which have a strong covalent character versus the typical solids, metallic or I would say inorganic solids.
So which two kinds of materials? There are going to be differences.
The ones that have a strong covalent character in their bonding, directional bonds, basically, right? So the electronic structure is quite different from the others. And so there seems to be two types of diagrams in there. Do you know, have you noticed this? Has anyone noticed this? Or could it be important?
I guess all I can say, I'm going to say something more general than you probably want to hear. But if you look at the low pressure undoped side, there are many, many different things that are going on there, right? You can have just a bad metal. You could have, all kinds of things. You can have semiconductor-like behavior. So that's just an evidence that, even though they basically pretty much all have the same phase diagram, when you get down to the details, the mechanism is going to be different and what's causing all this. So in other words, YBCO will not have the same mechanism as cerium, cobalt, and DIM5. It's just not the same mechanism. And if I had time to show you, it looks like the pairing mechanism in cerium, cobalt, and DIM5 is condo scattering. So even among the heavy fermions, and we can talk about that later, but they're really different. And I just like to point out, people don't like to hear that because they want Occam's razor, they want one solution. But in fact, if you saw how TC fractaled out, there's just too many there. And they're talking about one cure for cancer. Well, there's not one kind of cancer. If you're going to look at different kinds of breast cancer, you're going to have very, very different kinds of therapies. And there's many, many kinds of cancers. There's not one cancer. The moonshot against cancer, as much as I love Joe Biden, you have to understand that it's very different. And I think that's going to help us solve and learn to create better materials, better superconductors, and better triplet superconductors, which are very hard to design, by understanding each one of these families. So that's my take-home message.
Thank you. Any other comment? Please.
I have a question on your last part of the talk that I found very interesting, the analogy with the deformation of gravity. So maybe, I'm not sure I understand. You think that this deformation can cause some form of pairing that is more stable than BCS or resist?
No, I'm saying is that no one ever guessed that it was a distortion in the space-time continuum that was the fundamental question of gravity. No one ever guessed that it was a distortion in the lattice, granted time-dependent, that caused superconductivity. It's just basically, I keep saying it's a fun analogy. It doesn't mean that. But it also, I've never had a chance to really look at this more carefully because there might be some ways to help understand these things. For instance, my friends that do quasi-classical theory, right, like Gordon Boehm or some more recent people, David Pines, they were not only studying superconductors and correlated systems in the 50s, they were also using the same equations to apply to the inside of neutron stars. So they're using the exact same equations to look at things that are 10 to the Avogadro's number different from each other in sizes or in energy scales. And so I'm not a theorist. I don't know how to make it any better. It's just a fun way to think about it, and it's to explain that this isn't, our questions in quantum materials isn't a Higgs boson, it isn't a moonshot, and it isn't a gravity wave. There's a lot of them, and one of the reasons I do this is to try to get across that it's really complicated, and we can stay with it. So.
Yeah, because there are works, for example, on graphene from Mediano, in which they show that if you have dislocation, so deformation in your system, then this behaves as an effective monopole. It creates a magnetic field that is like a magnetic field of the monopole, and this can lead to also effect of pairing for superconductors. So what you're saying is very interesting, and in fact it happens that deformation can be interpreted as emergent fields. So it was very interesting.
Thank you that's a great comment. Thank you very much.
I think Professor Geiger has not asked a question, neither made a comment, which is unusual. But if there is any other comment or question, this is the time to ask it.
The best thing is to discuss the issues when drinking something together with Laura.
Yeah, I'm feeling really scared that I'm keeping you from your cocktail. I'm really nervous about this, so.
Well, I think we have time. So this is Turkish hospitality, so we can extend and extend.
But there are also disadvantages doing this over drinking, because you may overdrink. So I'm not so sure.
I will be okay. So
okay.
Thank you very much, Laura. I think it's a great honor to have all the speakers, Valerie, Ahmet, and Hasan Mandal, Also myself, not too bad maybe. Okay, it's your turn now.
Okay, yes, please. I think we have a
Let
diploma.
us thank one more time to our speaker for the nice speech. And also I should present the certificate of attendance. It's necessary for reimbursement.
And we thank all the speakers of this session for making such a nice session. And hope the upcoming sessions will have also such a nice discussions we have here. Thank you very much for all.